Look up at the night sky. What do you see? Pinpricks of light, the gentle glow of the moon, the vast, silent emptiness between them. But that emptiness, that profound void, is an illusion. It is not empty at all. It is a cosmic ocean teeming with secrets, with questions that have haunted humanity since we first gazed upwards. The universe is the greatest mystery we will ever know, and as the astronomer Carl Sagan so beautifully put it, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. This video is an invitation to join that grand act of self-discovery, to venture into the shadows and pull back the curtain on reality's deepest puzzles. We are about to embark on a journey through 35 of the universe's most profound and perplexing enigmas. Each one is a vital piece of the cosmic puzzle, a clue that brings us closer to understanding not just where we came from, but what we are. What truths are waiting for us in the dark expanse between the stars? The answers will challenge everything you think you know about physics, reality, and our place in the grand scheme of things. We will confront the ghostly presence of dark matter, an invisible substance that holds galaxies together yet slips through our detectors unseen. We will listen for alien signals like the famous wow signal, a lone cry from the cosmos that vanished as quickly as it appeared. We will grapple with cosmic anomalies that defy explanation, from the unexplained drift of our own spacecraft to the strange, tumbling shape of our first interstellar visitor. This is more than just a list of facts. It is an expedition to the very frontiers of human knowledge. It is a story written in the language of gravity, light, and time. A story of a universe that is far stranger, more violent, and more beautiful than we could have ever imagined. So prepare to have your curiosity ignited and your sense of wonder restored. The journey begins now with a mystery that surrounds us, binds the galaxy together, and yet remains completely invisible to our eyes. This is the enigma of dark matter. Imagine you are in a room where the furniture is mysteriously rearranged overnight. Chairs slide, books shift on their shelves, yet you never see the hand that moves them. You can only observe the effects of a presence that remains stubbornly, completely hidden from view. This is the essence of our first great cosmic mystery, the enigma of dark matter. It is the invisible giant shaping the cosmos, a ghostly substance that makes up not a small fraction, but a staggering 27% of the entire universe. We cannot see it, touch it, or directly detect it with any instrument we have yet devised. Its existence is known to us solely through its relentless gravitational pull, a force that guides the destiny of galaxies yet leaves no other trace. The pioneering work of astronomer Vera Rubin in the 1970s provided the most compelling evidence for this unseen cosmos. By meticulously measuring the rotation speeds of stars within distant galaxies, she expected to find that stars on the outer edges, much like planets in our solar system, would orbit more slowly than those closer to the center. Instead, she discovered something astonishing. The stars at the galactic fringe were whipping around just as fast as those near the core. This flat rotation curve could mean only one thing. Each galaxy was embedded within a massive, invisible halo of matter, a halo whose gravity was keeping those outer stars from flying off into the void. As Rubin herself reflected, it revealed a universe where what we see is merely the tip of the iceberg, a universe dominated by the unseen. So, what is this mysterious substance? For decades, the leading candidates have been hypothetical particles. Weakly interacting massive particles, or WIMP, are thought to be heavy particles that interact only through gravity and the weak nuclear force, making them incredibly difficult to catch. Then there are actions, particles that are fantastically light but could exist in such immense numbers that their collective mass would be enormous. Scientists have built exquisitely sensitive detectors deep underground, shielded from cosmic rays, hoping to witness the rare collision of a dark matter particle with ordinary matter. Others search for indirect signals, like the unique light that might be produced if two dark matter particles were to annihilate one another in the depths of space. Yet, despite these heroic efforts, dark matter continues to evade us, its true nature remaining one of physics' most profound puzzles. The influence of dark matter, however, extends far beyond holding individual galaxies together. Its gravitational pull acts as the fundamental scaffold for the entire universe. In the early cosmos, slight clumps of dark matter served as gravitational seeds, pulling in ordinary gas and dust, eventually leading to the formation of the first galaxies and the vast cosmic web we observe today. Without this invisible framework, the universe as we know it would not exist. So we are left with a humbling thought. If the majority of the matter in the universe is completely invisible to us, what does that say about the limits of our perception? We are like beings who can feel the wind but cannot see the air, tracing the outlines of a hidden world that forms the very foundation of reality. And this unseen force is just the beginning of the story, because an even more baffling and dominant component is pulling the universe apart. But if the ghostly pull of dark matter is the force that builds the cosmic architecture, then what is the mysterious pressure that is tearing it all apart? Picture a balloon being inflated, but not at a steady pace. Instead, some unseen hand begins to pump air into it faster and faster, causing the rubber to stretch at an ever-increasing rate, threatening to pull the entire structure thin. This is the phantom of dark energy, the even more baffling counterpart to dark matter, and it is the dominant force in our universe, making up a staggering 68% of everything. While dark matter pulls with gravity, dark energy appears to push, acting as a repulsive force that is causing the very fabric of space to expand at an accelerating pace. This astonishing discovery, which completely upended our understanding of the cosmos, came from two independent teams of astronomers in the late 1990s. They were studying distant supernovae, using these exploding stars as cosmic mile markers to measure how the expansion rate of the universe has changed over time. Everyone expected to find that the gravitational pull of all the matter in the cosmos was slowing the expansion down. Instead, they found the opposite. The supernovae were fainter than expected, meaning they were farther away than they should have been if the expansion were slowing. The universe wasn't just expanding, it was speeding up. As one leading cosmologist on the project remarked, it was a result so shocking that they spent months checking and rechecking for errors, afraid to believe what the data was screaming at them. Their work earned them the Nobel Prize, not for confirming a theory, but for shattering one and revealing a universe far stranger than we had imagined. So what could possibly be causing this cosmic acceleration? The leading candidate is a concept that Albert Einstein himself introduced and then later dismissed as his biggest blunder, the cosmological constant. In his equations for general relativity, Einstein added this constant as a form of energy inherent to the vacuum of space itself, a fixed energy density that would counteract gravity and keep the universe static. When the universe was found to be expanding, he abandoned the idea, but now cosmologists have revived it. This vacuum energy, sometimes thought of as the energy of virtual particles popping in and out of existence, could be the source of the repulsive gravity we call dark energy. The problem is, when physicists try to calculate the theoretical strength of this vacuum energy, the number they get is astronomically, impossibly large, about 120 orders of magnitude too big. This colossal discrepancy is one of the worst in all of theoretical physics. This leads to an intense ongoing debate. Is dark energy truly constant, as the cosmological constant suggests, or does its strength change over time? Some theories propose a dynamic form of dark energy, often called quintessence, a field that could evolve and fluctuate. If dark energy is not constant, it could radically alter the ultimate fate of the cosmos. A constant force points toward a heat death, where the universe expands forever, becoming cold, dark, and dilute. But if dark energy grows stronger, it could lead to a big rip, where the repulsive force eventually becomes so powerful that it tears apart galaxies, solar systems, planets, and even atoms themselves in a final, catastrophic moment. Contemplating this forces us to ask a profound question. What is the destiny of a universe that is forever stretching itself apart, pushing its constituent parts into an ever-deepening isolation? The energy that shapes this cosmic destiny finds a strange and haunting echo in the signals that occasionally reach us from the depths, brief whispers that seem to defy explanation. Now picture a quiet evening in August 1977. At Ohio State University's Big Ear radio telescope, astronomer Jerry Amon is engaged in the meticulous task of reviewing reams of computer printout data, a routine search for any sign of an artificial signal from the cosmos. His eyes scan the columns of letters and numbers, most of it representing the background noise of the universe, and then he sees it, a sequence so unexpected, so powerful that it leaps off the page, 6EQUJ5. The signal intensity had risen to a level 30 times louder than the cosmic background static. In a moment of pure, unscripted astonishment, Amon circles the sequence in red pen and, in the margin, writes a single, heartfelt word that would forever name this enigma: wow. This was the wow signal, a burst of radio waves that lasted for 72 seconds, captured by the Big Ear telescope as it scanned a region near the constellation Sagittarius. It was a narrowband signal concentrated around the frequency of 1420 MHz, a quiet part of the radio spectrum that is naturally protected from interference and is considered a prime band for interstellar communication. Jerry Amon himself later reflected on its near-perfect characteristics. It was strong, it was focused, and it appeared exactly as scientists had predicted a deliberate, artificial signal from another world would look. It wasn't the scattered broadband emission of a quasar or a pulsar. It was a clean, sharp whistle in the cosmic static, a signal that seemed to shout, "I am here." Yet, as quickly as it arrived, it vanished. The most frustrating part of the mystery is that the signal was never heard again, despite numerous follow-up observations by Amon and other astronomers, and later projects that specifically targeted the same area of the sky. The airwaves remained silent. The wow signal was a one-time event, a solitary data point that continues to defy a definitive explanation. The very nature of the Big Ear telescope, with its two feed horns that scanned the sky slightly apart from each other, meant the signal should have been detected for 72 seconds by one horn, then, after a pause, another 72 seconds by the second horn. But the wow signal was only ever seen by one. This suggests the source was abruptly switched off, or it moved out of the telescope's field of view, adding another layer of intrigue. So what could have caused it? One of the more recent and debated natural explanations points to comets. In 2017, an astronomer proposed that the signal could have been generated by the hydrogen cloud surrounding a comet that happened to be passing through that precise region of the sky at that exact time. However, this hypothesis has been heavily criticized, as the comets in question were not actually in the right part of the sky when the signal was detected, and comets are not generally known to produce such intense, narrowband radio emissions. Other natural possibilities include a fleeting astronomical event, like a microlensing event that briefly amplified a distant background signal, or an unknown form of terrestrial interference that somehow bypassed all the telescope's filters. But each of these explanations feels strained, failing to fully account for the signal's unique profile. This leaves the most tantalizing, albeit unproven, possibility that the WOW signal was exactly what it appeared to be, a transient, targeted broadcast from an intelligent civilization. Perhaps it was a powerful radar beam from an alien spacecraft sweeping past our solar system for a mere moment. Or maybe it was a deliberate beacon, a hello aimed into the galaxy, and our planet simply drifted through its path for 72 glorious seconds before moving on. The signal's brevity could mean we caught a fragment of a longer message, or that the sending civilization only transmits in short bursts to conserve energy. We are left with a profound and haunting question. Was the WOW signal a fleeting, unintentional glimpse of another intelligence going about its business, or was it a natural cosmic phenomenon so rare that we have yet to witness it again? This singular, unrepeated event stands in stark contrast to the next class of cosmic signals, which are not lonely cries but persistent, repeating patterns that flash across the sky with immense power. If the WOW signal was a solitary shout in the cosmic dark, then fast radio bursts are the universe's strobe lights. Imagine a pitch-black sky where, for just 1,000th of a second, a flashbulb of radio energy goes off with the power of 500 million suns. These are not the slow, drawn-out whispers of distant quasars. They are millisecond-long screams, intense pulses of radio waves that have traveled across billions of light-years to reach our telescopes. First uncovered in 2007 by astronomer Duncan Lorimer and his team while they were sifting through archived data from the Parkes Radio Telescope in Australia, the initial reaction was one of profound skepticism. The signal was so bright and so brief that many wondered if it was merely a glitch, an artifact of terrestrial interference from a microwave oven on the observatory grounds or a passing satellite. But as more of these bursts were detected by other telescopes around the world, the astronomical community had to accept a stunning new reality. The cosmos was punctuated by these incredibly powerful, transient events. What makes fast radio bursts even more fascinating is that they are not all the same. Most are one-off events, a single, spectacular flash that never repeats, leaving astronomers scrambling to point other instruments at the location long after the echo has faded. But then there are the repeaters. The most famous of these, designated FRB 1211-2, was a game-changer. Discovered in 2015, this source, located in a tiny dwarf galaxy 3 billion light-years away, pulses intermittently, sometimes remaining quiet for months before unleashing a flurry of bursts. This repetition was a crucial clue, effectively ruling out theories that involved a single, cataclysmic destruction of an object, like a star being torn apart by a black hole. Instead, it pointed toward a source that could survive these immense energy releases, something that was capable of firing off multiple shots. So what cosmic engine could possibly produce such focused, staggering amounts of energy? The leading suspect today is a type of neutron star known as a magnetar. These are the universe's ultimate magnets, stellar corpses with magnetic fields so powerful they could erase a credit card from halfway to the moon. Theorists suggest that a starquake on the surface of a magnetar, a sudden cracking of its ultra-dense crust, could unleash a titanic shockwave, rippling through the magnetosphere and releasing a blistering flash of radio waves. This model fits the bill for the one-off bursts perfectly. For the repeating FRBs, the mechanism might be different, perhaps a magnetar in a particularly active phase, or one orbiting a companion star whose material periodically fuels the eruptions. Other compelling theories point to the mergers of incredibly dense objects, like two neutron stars spiraling into each other, which could create a one-time, ultra-energetic blast. And while considered a less likely possibility, some have even proposed that these bursts could be the byproduct of advanced technology, such as the power beams of immense light sails pushing alien spacecraft across the galaxy. The immense challenge for scientists lies in the very nature of these events. They are incredibly brief, often lasting less time than the blink of an eye, and they appear randomly from any point in the sky. Catching one is like trying to photograph a specific lightning bolt during a global storm. You have to be looking in exactly the right place at exactly the right time. Modern observatories are now using sophisticated software to scan the sky in real time, sending out instant alerts when a burst is detected, hoping to catch the aftermath in other wavelengths like X-rays or optical light. But by the time the alert goes out, the burst itself is already ancient history. To truly understand them, we must imagine the sheer violence required. An event that, in a fraction of a second, can outshine entire galaxies. It forces us to confront a universe that is not only vast and beautiful, but also capable of sudden, unimaginable ferocity. While these bursts represent the universe's most transient and violent signals, they stand in stark contrast to another class of cosmic object that offers the opposite extreme, a steady, metronomic beat of incredible reliability. Amid the chaotic symphony of the cosmos, where gamma-ray bursts scream and supernova flare, there exists a rhythm of astonishing precision. It is the steady, metronomic ticking of a cosmic clock, a pulse so regular that its consistency can rival the most advanced atomic timekeepers we have built here on Earth. And yet, this impeccable timing does not come from a delicate machine in a vacuum chamber, but from the furious spin of a city-sized object, a stellar corpse rotating hundreds of times every second, whipping through space with the mass of a sun compressed into a sphere no larger than Manhattan. These are pulsars, the lighthouses of the galaxy, and their discovery is a story that begins not with a seasoned professor, but with a sharp-eyed graduate student who stumbled upon one of the greatest astronomical mysteries of the 20th century. In the late 1960s, a young Jocelyn Bell Burnell was helping to build a new radio telescope at Cambridge University, a forest of wooden poles and wires designed to study the twinkling of distant quasars. As she meticulously analyzed the miles of chart paper churned out by the instrument, she noticed a peculiar signal, a faint, rhythmic pulse that appeared and disappeared with the steady march of the stars. It was so precise, so artificial-looking that she and her supervisor, Anthony Hewish, half-jokingly labeled it LGM-1 for Little Green Men. The notion of an alien civilization sending a deliberate beacon was a serious, if thrilling, possibility. What else could produce such a perfectly timed signal? A rapid-fire series of beeps repeating every 1.337 seconds, sweeping past Earth like a cosmic searchlight. What Bell Burnell had discovered was not an extraterrestrial broadcast, but something almost as wondrous, a rapidly spinning neutron star. A neutron star is the incredible remnant of a supernova explosion, a core so compressed that protons and electrons are forced together to form neutrons, creating matter of unimaginable density. Just a sugar cube-sized piece of this material would weigh as much as a mountain. As this stellar cinder spins, its powerful magnetic field, trillions of times stronger than Earth's, acts like a colossal generator, accelerating particles that then beam out intense radiation from the magnetic poles. If these poles are misaligned with the star's rotation axis, the beams sweep through space like the light from a lighthouse, and when that beam flashes across our line of sight, we see a pulse. The discovery earned a Nobel Prize, though controversially awarded only to Hewish, overlooking Bell Burnell's crucial role, a historical footnote that highlights the challenges faced by women in science at the time. The extreme nature of pulsars makes them far more than just celestial curiosities. They are unparalleled natural laboratories for testing the laws of physics under conditions we could never recreate on Earth. When two pulsars orbit each other, as in the famous binary pulsar discovered by Russell Hulse and Joseph Taylor, they provide a perfect testbed for Einstein's theory of general relativity. The intense gravitational field causes the orbits to slowly decay, emitting energy in the form of gravitational waves, ripples in spacetime exactly as predicted. The timing of these pulses is so exquisitely sensitive that it allowed for the first indirect detection of gravitational waves, a discovery that would later be confirmed directly and earn its own Nobel Prize. In this way, pulsars serve as our cosmic watchmakers, their ticks and tocks allowing us to probe the very fabric of reality. Yet, even these paragons of regularity hold a deep-seated mystery. Occasionally, a pulsar will experience what astronomers call a glitch, a sudden, tiny, but very real increase in its spin rate. It's as if a perfectly tuned watch suddenly, inexplicably, started ticking faster for a moment. These glitches are windows into the bizarre interior of a neutron star. Theorists believe that beneath a solid crust of iron nuclei, the interior is a superfluid, a state of matter that flows without any friction. This superfluid of neutrons spins independently. As the pulsar's rotation gradually slows down over millennia, the superfluid core can become unstuck from the crust, transferring a burst of angular momentum that gives the star a sudden speed boost. These events hint at a complex and violent inner world, a realm of physics we are only beginning to comprehend. The existence of such perfect cosmic timekeepers forces us to wonder. If pulsars had not been so bright in radio waves, would we have ever found them? What other rhythms and patterns are hidden in the cosmos, encoded in gravitational waves, neutrino fluxes, or some medium we have not yet learned to perceive? The universe is likely filled with clocks of all kinds, ticking away in the darkness, each one a key to unlocking a new law of physics or revealing a new type of object. The steady, predictable beat of a pulsar offers a moment of order in a universe often defined by chaos, a reassuring signal that even in the aftermath of stellar death, there can be a profound and beautiful precision. And this very order stands in stark opposition to the turbulent, messy, and violent processes that give these stellar corpses their life in the first place. But for all the precision of these stellar clocks, their creation is a story of magnificent chaos. To find the birthplace of stars, we must turn our gaze away from the brilliant points of light and towards the dark, silent patches that stitch the Milky Way. These are not empty voids, they are cosmic wombs, vast clouds of cold gas and dust so thick they blot out the starlight from behind. Within these frigid, shadowy realms, hidden from visible light, the secret lives of star nurseries unfold. It is here, in the deep cold and darkness, that gravity performs its most delicate act, coaxing scattered atoms to coalesce into the brilliant furnaces that will one day illuminate the void. The most famous of these nurseries, the Orion Nebula, appears to our eyes as a beautiful, glowing cloud. But that glow is merely the light from a few newborn stars heating up the gas around them. The true action is hidden within the opaque, dark molecular clouds that surround it, where thousands of new suns are in the process of being built. The fundamental mystery of these nurseries lies in the trigger. We know that a cloud of gas must collapse under its own weight to form a star, but what tips the balance? What causes a cloud that has been stable for millions of years to suddenly begin its inward fall? The answer is not simple, and it involves a delicate and complex cosmic tug of war. Astrophysicists describe a constant battle within the cloud. On one side is gravity, the great unifier, always trying to pull everything together. Pushing back is gas pressure, the thermal energy of the molecules that wants to keep the cloud puffed up. But there are other, more subtle players. Turbulence, the churning motion within the cloud, can create dense pockets that become the seeds for collapse, but it can also stir the cloud up enough to prevent it from settling. Then there are magnetic fields, invisible lines of force that thread through the cloud like cosmic threads, providing a supporting structure that can effectively prop up the gas against gravity's pull. As one leading researcher put it, it's a wonder stars form at all. The cloud has to be just cold enough, just dense enough, and just perturbed enough for gravity to finally win. When gravity does triumph, it doesn't just create one star, it spawns an entire family, and this leads to another deep-seated puzzle known as the initial mass function. It turns out that star formation is not a random process. Whenever a giant molecular cloud collapses, it produces a remarkably consistent distribution of stellar sizes. For every massive, brilliant star that forms, it creates a larger number of medium-sized stars like our Sun, and a veritable multitude of tiny, faint red dwarf stars. This pattern, this cosmic recipe for building stellar populations, is seen again and again across our galaxy and in others. Why does nature follow this specific rule? Why isn't it a free-for-all, with some clouds making only giants and others only dwarfs? The answer likely lies in the intricate physics of fragmentation. As a large cloud collapses, it doesn't do so as a single monolith. It breaks apart into smaller and smaller clumps, like a collapsing ceiling giving way in sections. The turbulence and density fluctuations within the cloud seem to dictate how it shatters, setting the budget for how many stars of each mass will be born. It's a universal law of star production that we can observe but do not yet fully understand. The story doesn't end once a star ignites. The newborn stars themselves become powerful agents of change, a process astronomers call feedback. The most massive stars that form are incredibly luminous, flooding their surroundings with intense ultraviolet radiation. This radiation heats the surrounding gas, increasing its pressure and effectively blowing away the very material that could have collapsed to form more stars. At the same time, these stars generate powerful winds, streams of charged particles that carve out vast bubbles in the nebula. This feedback can brutally shut down star formation in its immediate vicinity, sterilizing the nursery. But in a beautiful twist of cosmic irony, this destructive force can also be creative. The shock waves from these winds and from subsequent supernova explosions can slam into nearby, undisturbed clouds of gas, compressing them and triggering a new wave of collapse. So, a star's birth can spell the end for its siblings, but it can also be the midwife for a whole new generation of stars in a neighboring cloud. It is a cycle of creation and destruction that governs the rhythm of galactic evolution. Contemplating this violent, beautiful process brings it home in a very personal way. Our own Sun, the steady, life-giving star at the center of our solar system, was once just a nameless protostar in a similar nursery over 4.5 billion years ago. It was not a first-generation star. The cloud it formed from was enriched with heavy elements forged in the hearts of previous generations of stars that lived and died spectacularly. The same feedback processes that cleared out the nebula around it likely determined the final architecture of our planetary system. The formation of a star is just the first step in a life cycle of cosmic proportions. A life cycle that, for the most massive stars, ends in the very same spectacular violence that can trigger new beginnings. We have explored the violent nurseries where stars are born, But now we must confront a motion that encompasses our entire galaxy. It is a deeply unsettling thought. Our Milky Way, a vast spiral of hundreds of billions of stars, is not simply adrift in the cosmos. It is being hauled with irresistible force towards a specific point in the darkness, a gravitational focal point that we cannot directly see. This is the mystery of the Great Attractor, a colossal anomaly in the fabric of space whose presence we can only infer from the silent, relentless flow of galaxies around us. It acts as a hidden anchor for our entire local corner of the universe, pulling us and our neighboring galaxies toward a destination in the constellation Centaurus. This grand cosmic drift was first uncovered in the 1970s and 80s, when astronomers began to meticulously map the velocities of galaxies. By measuring their redshifts, the stretching of light waves as objects move away from us, they could plot the general expansion of the universe. However, they soon noticed something peculiar. Galaxies were not simply receding in a perfectly smooth, uniform flow. There was a distinct deviation, a bulk motion. Our local group of galaxies, including the Milky Way and Andromeda, along with the entire Virgo supercluster we belong to, was all moving in the same direction at a staggering speed of over 600 kilometers per second. It was as if every ship in a vast flotilla was being pulled by a powerful, unseen current. This discovery revealed that the expansion of the universe is just the backdrop. Superimposed upon it are these great rivers of galactic motion, driven by the gravitational tug of immense concentrations of mass. The central challenge in solving this mystery is a deeply frustrating one of perspective. The direction of this pull points towards a region of the sky that lies in what astronomers call the zone of avoidance. This is not a mystical term, but a very practical one. It refers to the plane of our own Milky Way galaxy, a thick band of stars, gas, and dust that encircles us. When we look towards the center of our galaxy, we are looking through a crowded, dusty fog that obscures our view of the distant universe beyond. It is like trying to see a distant mountain range while standing in the middle of a dense, brightly lit forest. The very heart of the Great Attractor lies hidden behind this brilliant, obstructive veil, making direct observation with optical telescopes nearly impossible. So what is pulling us? The prevailing theory is that the Great Attractor is not a single, monstrous object, but a massive supercluster of galaxies, an immense knot in the cosmic web where the gravitational pull of thousands of galaxies combines into one powerful draw. Observations that can pierce through the galactic dust, such as infrared and radio surveys, have begun to map this hidden realm. They have revealed a significant concentration of mass in that direction, known as the Norma cluster, which is likely the core of this larger attractor region. But there is a growing sense that the story is even bigger. The pull we feel may not be from the Great Attractor alone, but from something beyond it, something even more immense. This leads to the concept of the Laniakea supercluster, a Hawaiian word meaning immeasurable heaven. Our entire local group of galaxies, including the Virgo supercluster and the Great Attractor itself, appears to be just a single branch of this vast cosmic structure, all flowing towards a gravitational center far grander than we initially imagined. This realization forces us to ask a humbling question: what other colossal architectures, what other unseen leviathans of mass are shaping the motion of our galaxy from the hidden depths of space, completely invisible to our direct gaze? For centuries, we pictured the universe as a mostly random scattering of stars and galaxies, a brilliant but disorganized splash of light across the canvas of space. But that image is fundamentally wrong. The true architecture of the cosmos is something far more structured, far more beautiful, and on a scale so vast it challenges human comprehension. We live within a cosmic web, a sprawling, intricate network of galaxies strung along vast filaments of dark matter like pearls on an invisible string. These filaments stretch across the unimaginable emptiness, connecting at dense nodes where immense clusters of thousands of galaxies swarm together. Between these threads lie the voids, caverns of near-nothingness so enormous they could contain thousands of galaxy groups with room to spare. This is not chaos, this is the grand design of the universe, a blueprint written by the gravitational hand of dark matter and traced in the light of billions of suns. The very existence of this web is a direct consequence of the unseen universe we began with. The dark matter that holds individual galaxies together also acts as the cosmic architect on the largest scales. In the early universe, tiny quantum fluctuations in the dense, hot soup of matter and energy were stretched to enormous sizes by a period of rapid inflation. These minute ripples in density became the seeds for all future structure. The slightly denser patches had a bit more gravitational pull, slowly drawing in more dark matter from the surrounding areas over billions of years. As one leading cosmologist described it, using powerful supercomputer simulations, you can watch this evolution unfold. The dark matter forms a delicate, frothy structure first, a scaffold upon which ordinary matter, the gas that would eventually form stars and galaxies, could later condense. The simulations show a universe evolving from a nearly smooth beginning into the complex, web-like tapestry we observe today, a process driven almost entirely by the gravitational influence of the invisible majority. This cosmic architecture dictates where galaxies can and cannot live. The great intersections of dark matter filaments are the metropolitan centers of the universe, where giant galaxy clusters reside, each a bustling hive of stellar activity. The filaments themselves are the cosmic highways lined with galaxies in a long, winding procession. But the voids, the empty spaces between the threads, are perhaps the most mysterious component. These are not just slightly emptier regions, they are profoundly desolate. The Boötes Void, for instance, is a spherical region about 330 million light-years across, yet it contains only a few dozen galaxies where you would expect to find thousands. A void is not a perfect vacuum. It contains a very thin, hot gas, but it is a place where the process of galaxy formation seems to have been almost entirely shut down. This leads to a central mystery of the cosmic web. Why are the voids so empty? What physical processes actively prevent galaxies from forming in these immense regions? The answer seems to lie in the initial conditions set in the early universe. The voids started as regions of slightly lower density. While gravity was pulling matter into the filaments and nodes, it was simultaneously pulling matter out of the voids, making them even emptier over time. It is a cosmic case of the rich getting richer and the poor getting poorer. Furthermore, any gas that did remain in a void would be so diffuse that it couldn't easily cool and collapse to form stars. And for any fledgling galaxy that did manage to start forming, the immense gravitational pull of the surrounding web would likely have drawn it out of the void and towards the nearest filament, leaving the central regions barren. The few galaxies that do stubbornly exist within the voids, often called void galaxies, are fascinating objects in their own right, evolving in isolation away from the violent interactions common in clusters, potentially giving them a quieter, more predictable history. To truly grasp the scale of this structure is to confront our own profound smallness. Our Milky Way galaxy is not at a special node or intersection. We reside within a filament, a part of the Laniakea supercluster. From our perspective, we are on a single thread of the web, a speck within a structure that is one of many in the observable universe. Contemplate this: the cosmic web is the largest pattern known to exist. The distance from one side of a large void to the other can be 500 million light-years. This means that if we could travel at the speed of light, it would take us 500 million years just to cross an empty space. This vast architecture, built over 13.8 billion years, is the ultimate expression of gravity's patient work. It is a structure that emerged from the faintest whispers of the Big Bang, a permanent monument to the universe's first moments, which themselves hold mysteries that take us to the very edge of physics. After the grand architecture of the cosmic web was established by the gravitational pull of dark matter, the universe entered a profound and silent chapter. For millions of years following the fade of the Big Bang's afterglow, the cosmos was a truly dark place. There were no stars, no galaxies, no sources of visible light. The universe was a vast, expanding sea of hydrogen and helium gas, laced through with the invisible threads of dark matter. It was a simple, elemental, and profoundly empty cosmos, waiting for a spark to break the monotony and begin the long process of building complexity. That spark would come from the very first stars, a generation of celestial giants so different from anything that exists today that they are known by a special classification, population 3 stars. These are the elusive pioneers of the cosmos. They were the first objects to condense out of the primordial gas, and because of this, they were made of a perfectly pure, pristine material. There were no heavy elements like carbon, oxygen, or iron, the elements that form planets and life, because those elements did not yet exist. They had to be forged somewhere. This unique composition had a dramatic effect on the stars themselves. Without heavier elements to help the gas cool and fragment efficiently, the collapsing clouds of hydrogen and helium could grow to immense sizes before they ignited. Theoretical models suggest that population 3 stars were not just large, they were behemoths, true cosmic titans that could have been hundreds, even 1,000 times more massive than our own sun. Imagine a star so massive that its surface temperature would be blisteringly hot, radiating most of its energy not as visible light, but as intense, high-energy ultraviolet radiation. Their lives would have been spectacularly brief and violent. A star like our Sun has a lifespan of about 10 billion years, steadily fusing hydrogen into helium in its core. But a population 3 star, with its tremendous mass creating immense gravitational pressure, would burn through its nuclear fuel at a ferocious rate. It would live for only a few million years, a mere cosmic blink, before meeting a cataclysmic end. Their deaths would not be ordinary supernova. They would be hypernova, explosions of such unimaginable power that they would outshine entire galaxies, blasting the newly forged heavy elements out into the surrounding void for the very first time. This is precisely why the hunt for these first stars is so crucial, and why their elusiveness is such a compelling mystery. We have strong indirect evidence that they must have existed. The oldest stars we can observe, known as population 2 stars, contain trace amounts of heavy elements. This tells us they formed from gas that had already been seeded by a previous generation. But we have never directly seen a true population 3 star. The reason is simple: they lived fast, died young, and are now incredibly far away in both space and time. Their light has been traveling for over 13 billion years to reach us, stretched into the infrared part of the spectrum by the expansion of the universe, and rendered incredibly faint. This is where our most powerful new eye on the cosmos enters the story, the James Webb Space Telescope. Unlike Hubble, which sees primarily invisible and ultraviolet light, Webb is an infrared telescope specifically designed to peer back into this era of cosmic dawn. Astronomers are using it to scan the deepest fields of the sky, looking for the distinct chemical fingerprint of a galaxy lit by these first stars. A population 3 star would have a unique signature, a spectrum almost completely devoid of the heavy element lines that are commonplace in the light from younger stars. Finding even a single small galaxy dominated by this pure primordial light would be a discovery of Nobel Prize-winning significance, confirming a key chapter in our cosmic origin story. The importance of this search goes far beyond simply ticking a box in a theoretical model. The death of these first stars set the entire cosmic cycle in motion. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the hearts of stars that lived and died long before our sun was born. But the very first atoms of these elements, the seeds from which all subsequent chemistry grew, were created in those initial universe-altering hypernovae. By studying the chemical signature of these first explosions, we are reading the recipe for our own existence. It forces us to ask a profound question. Did the specific nature of these first stars, their immense size and violent deaths, create the precise conditions necessary for rocky planets and ultimately life to form? The end of these stellar giants did more than just enrich the cosmos. It set the stage for an even more enigmatic class of objects to emerge from the ashes, the universe's first black holes. The violent, brilliant deaths of the first stars did more than just seed the universe with the elements for life. They may have also planted the seeds for the most monstrous objects in the cosmos. We now encounter a profound paradox that challenges our understanding of cosmic evolution. Astronomers, using telescopes like the James Webb, are finding quasars, supermassive black holes powering incredibly bright galaxies that existed when the universe was less than 1 billion years old. These are not just any black holes, they are behemoths weighing billions of times the mass of our sun. And here lies the puzzle. How did something so colossal have time to grow so big so fast? It's like finding a fully grown ancient redwood tree in a forest that is only a few years old. The standard model of black hole growth, where a stellar mass black hole slowly accumulates material over billions of years, simply doesn't work on this timescale. These monsters were born, or at least grew up, in a cosmic blink, and their existence forces us to consider far more dramatic birth scenarios. These supermassive black holes, or SMBHs, are not rare anomalies, they are the rule. They reside at the gravitational heart of nearly every large galaxy we can see, including our own Milky Way, which hosts a relatively quiet 4 million solar mass black hole named Sagittarius, a star. But the early universe quasars are a different breed altogether. They are these engines in their extreme youth operating at full throttle. As one leading astrophysicist studying these objects remarked, "It's like discovering a toddler who is already 7 feet tall and can lift a car." The laws of physics as we understand them seem to strain under the weight of explaining how this is possible. The sheer speed of their formation points to a universe where the initial conditions for growth were radically different from the more sedate environment we see today. This puzzle leads scientists to 2 primary dramatic theories for how these giants got their start. The first involves the ultimate stellar death. Imagine a population 3-star, one of those first-generation behemoths hundreds of times more massive than the Sun. When such a star reaches the end of its short life, it might not just go supernova. It could undergo a phenomenon known as direct collapse. Instead of exploding, the entire star could implode under its own immense gravity, skipping the supernova stage entirely and collapsing directly into a black hole with a starting weight of perhaps 100 solar masses or more. This gives the black hole a huge head start, a massive seed from which to grow. The second, even more extreme theory is the direct collapse of a giant gas cloud. In the dense early universe, a massive primordial cloud of gas, perhaps destabilized by the intense radiation from nearby first stars, could have collapsed without ever fragmenting to form stars at all. This monolithic collapse could create a seed, black hole of tens of thousands of solar masses right out of the gate. These two scenarios represent a universe playing by different, more intense rules than those we see in our modern cosmic neighborhood. This mystery then bleeds into a fundamental chicken and egg problem for galaxy formation. Which came first, the galaxy or the supermassive black hole at its center? Does a galaxy form first, and its central density of stars and gas naturally funnels material into a growing black hole? Or does a massive black hole form early on, and its immense gravitational pull act as a nucleus around which the entire galaxy assembles? The evidence we have suggests a deeply intertwined co-evolution. Observations show a surprising correlation between the mass of a galaxy's central bulge of stars and the mass of its supermassive black hole. Larger bulges host larger black holes. This tight relationship implies that the growth of the black hole and the growth of the galaxy are linked, perhaps through the same inflows of gas that fuel both star formation and the black hole's appetite. They may have grown up together, each regulating the other through powerful feedback mechanisms like radiation and jets from the active black hole that can heat gas and shut down further star formation. A key to solving this growth mystery may lie in finding the missing links, black holes of intermediate mass, between a few hundred and a few 100,000 times the mass of the Sun. For a long time, our catalogue of black holes had a gap. We knew of small stellar mass black holes and giant supermassive ones, but the intermediate steps were elusive. Recently, however, evidence for these intermediate mass black holes, or IMBHS, has been mounting. They have been found lurking in the heart of some globular clusters, dense swarms of stars orbiting galaxies, and there are tantalizing signs of them in the centers of some dwarf galaxies. These objects could be the long-sought seeds that grew into the supermassive giants, fossils from an era when black holes were still in their adolescent growth spurt. Finding and studying them is like finding a crucial chapter in a history book that was previously torn out. Contemplating the origin of these cosmic monsters forces us to reimagine the infancy of the universe. It was not a gentle place. It was a violent, dense, and incredibly fertile environment, where physical processes occurred at intensities we can scarcely replicate in our simulations. The rapid appearance of supermassive black holes is a direct testament to this ferocious beginning, a signature of a cosmos that built its largest structures in a frantic rush. The sheer power locked within these gravitational giants is not just theoretical. It becomes terrifyingly apparent when they feed, unleashing some of the most energetic phenomena since the Big Bang itself. If the explosive birth of supermassive black holes showcases the violent infancy of the cosmos, then gamma-ray bursts are the universe's ongoing temper tantrums. These are not merely large explosions, they are the single most energetic events known to occur since the Big Bang itself. In a span of time shorter than a heartbeat, a gamma-ray burst can unleash more energy than our Sun will radiate over its entire 10 billion-year lifespan. All of that power is concentrated into a focused beam of high-energy gamma rays, a flash of light so intense that it can, for a few fleeting seconds, outshine every star in every galaxy in its observable universe combined. They appear without warning from random directions in the sky, flash brilliantly, and then vanish forever, leaving behind only a fading afterglow and a profound mystery for astronomers to unravel. The story of their discovery is a perfect example of scientific serendipity, born from the geopolitical tensions of the Cold War. In the late 1960s, the United States launched the Vela satellite series, a fleet of unmanned spacecraft designed with one primary mission: to monitor the heavens for the telltale gamma-ray signature of clandestine nuclear weapons tests in violation of the Atmospheric Test Ban Treaty. The satellites were not pointed at the stars, they were watching Earth. But in 1967, the Vela satellites detected something completely unexpected, a brilliant flash of gamma radiation that did not come from our planet. It came from deep space. Perplexed, the scientists working on the project, led by Ray Klebisadel, spent years carefully analyzing the data, ruling out any terrestrial or solar origin. They had stumbled upon a phenomenon of cosmic proportions, a discovery so significant it was kept secret for years while the team verified their results. When the findings were finally published in 1973, they unveiled a new and terrifying class of astronomical object that no one had predicted. As more bursts were catalogued, a clear pattern emerged, leading to a crucial classification. Gamma-ray bursts are not all the same. They come in two distinct flavors, each telling a different story of cosmic catastrophe. The first type are the long-duration bursts, which last anywhere from 2 seconds to several minutes. These are the true death cries of the most massive stars in the universe. When a star dozens of times more massive than our Sun exhausts its nuclear fuel, its core can no longer support itself against its own immense gravity. It collapses catastrophically, not into a neutron star, but directly into a black hole. In this incredibly violent transition, a fraction of the star's mass is not swallowed. Instead, it is whipped into a swirling, superheated disk around the newborn black hole, and through processes we are still striving to understand, twin jets of material are launched from the poles at velocities approaching 99.99% of the speed of light. These jets, blisteringly hot and focused, punch their way out through the outer layers of the dying star. The interaction within these jets produces the initial pulse of gamma rays, the burst we see. The stellar explosion that follows is not a typical supernova. It is a hypernova, an event orders of magnitude more powerful, and it is this event that creates the longer-lasting afterglow we can study across other wavelengths. The second type, the short-duration bursts, are even more fleeting, typically lasting less than 2 seconds. Their origin is equally dramatic but involves a different kind of cosmic demolition derby. These bursts are believed to be the signature of two ultra-dense stellar corpses, neutron stars, spiraling together in a final, fatal dance. For millions of years, a binary pair of neutron stars loses energy through the emission of gravitational waves, their orbits slowly decaying until they finally merge. When they collide, the result is spectacular. The merger can form a black hole almost instantaneously, surrounded by a dense, hot torus of neutron-rich material. Just as in the long bursts, this system can power incredibly focused jets for a brief period, producing the short, sharp flash of gamma rays. These events are also thought to be the primary factories for the heaviest elements in the universe, like gold and platinum, forging these precious metals in the furious aftermath of the collision and scattering them across the galaxy. The central, enduring mystery of both types of bursts is the nature of the central engine. How does a collapsing star or a merging binary system take so much gravitational energy and focus it so efficiently into such narrow, relativistic jets? It is a physics problem of staggering complexity, involving extreme magnetic fields, neutrino physics, and the behavior of matter at densities far beyond what we can create in any laboratory. Scientists use sophisticated computer simulations to model the chaotic moments after a core collapse or a merger, trying to understand how the magnetic fields become wound up like cosmic springs, channeling the outflow and accelerating particles to near light speed. The engine must operate with incredible precision and power to avoid simply blowing the system apart in a spherical explosion. Instead, it creates a surgical strike of energy, a cosmic blowtorch that is only visible if one of its beams is pointed directly at Earth. This beaming effect also explains why we see bursts from so far away. The energy is not wasted in all directions but is concentrated into a searchlight, making them visible across billions of light years. This incredible power, however, comes with a sobering implication. What would happen if a gamma-ray burst were to occur relatively close to our own galaxy, perhaps within a few thousand light years? The consequences would be dire. If one of the jets were aimed at Earth, the initial blast of gamma rays would violently interact with our atmosphere. It would strip away the ozone layer, the planet's protective shield against ultraviolet radiation from the sun. This would subject the Earth's surface to intense, DNA-damaging UV light, potentially triggering a mass extinction event. Some scientists have even speculated that a gamma-ray burst could have been responsible for the Ordovician extinction event 440 million years ago, which wiped out a significant portion of marine life. It is a chilling reminder that the universe is not a static backdrop. It is a dynamic and sometimes dangerous place where events occurring millions of light years away can hold implications for the survival of life on any world. While gamma-ray bursts represent the universe's most instantaneous and dramatic displays of power, there are other cosmic mysteries that unfold with a subtlety that is equally profound, revealing themselves not in a flash but in a slow, patient drift. While gamma-ray bursts represent the universe's most cataclysmic explosions, a far more subtle mystery was unfolding much closer to home, hidden in the precise trajectory of two robotic ambassadors venturing into the void. The story of the Pioneer Anomaly begins with two intrepid spacecraft, Pioneer 10 and Pioneer 11, which launched in the early 1970s. Their missions were triumphs of engineering, performing the first flybys of Jupiter and Saturn, and then continuing on trajectories that would eventually carry them out of the solar system entirely. For decades, scientists at NASA, a jet propulsion laboratory, meticulously tracked their progress by monitoring the faint radio signals sent back across billions of miles. By measuring the Doppler shift in these signals, the tiny change in frequency caused by the spacecraft's motion, they could calculate their velocity and position with incredible accuracy. It was through this painstaking work that they noticed something peculiar, a tiny, persistent whisper in the data that refused to go away. Both spacecraft were experiencing a minute but constant deceleration, an almost imperceptible tug pulling them back towards the sun. This force was incredibly small, roughly 10 billion times weaker than the gravity we feel on Earth's surface, equivalent to the gentle pressure of a single grain of sand resting on your hand. Yet, over the vast distances the pioneers were traveling, this tiny effect accumulated into a significant deviation from their predicted paths. As one project scientist involved in the analysis later reflected, "We checked everything. We looked for every conceivable mundane explanation. Was it the gentle push of the solar wind? Was there a tiny leak from a thruster? Could it be the pressure of sunlight itself?" Each of these possibilities was investigated and ruled out. The anomaly was real, and it was baffling. Here was an effect that was not predicted by Newton's laws of motion or Einstein's theory of general relativity. A tiny flaw in our understanding of gravity playing out on a grand interstellar scale. The persistence of this unexplained drift ignited the imaginations of theoretical physicists around the world. If it wasn't a simple engineering issue, then it had to be a sign of new physics. Some proposed modifications to Einstein's theory of gravity itself, suggesting that our understanding of how gravity works over very large but very weak scales might be incomplete. Perhaps a new term was needed in the equations, a fifth force that would only become noticeable in the deep, weak gravity environment of the outer solar system. Other, more exotic theories suggested that the pioneers might have sailed through a local clump of dark matter, whose gravitational pull was providing the extra tug. There was even speculation about the influence of unseen mass in the Kuiper belt or the gravitational pull from the galaxy as a whole. For a time, the Pioneer Anomaly stood as a tantalizing hint that our most fundamental theories might need a tweak, a clue that the laws of physics as we knew them were not the final word. The mystery, however, would not be solved by grand new theories, but by an exhaustive and brilliant piece of detective work focused on the spacecraft themselves. A team of researchers led by Slava Turyshev dedicated years to recovering old telemetry data and building incredibly detailed thermal models of the Pioneer spacecraft. They realized that the probes were powered by radioisotope thermoelectric generators, which produced heat as a byproduct of radioactive decay. This heat had to be dissipated into space to keep the instruments from overheating. The spacecraft were designed with a specific geometry. Their main antennae were always pointed directly at Earth, which meant that the bulk of the spacecraft body acted as a shield, radiating heat preferentially away from the Earth. The team's sophisticated model revealed that this radiated heat was not perfectly symmetrical. A tiny, anisotropic fraction of these photons, these particles of heat energy, was being emitted from the back of the spacecraft's main dish. According to the simple law of conservation of momentum, every photon carrying energy away from the spacecraft imparted a minuscule amount of thrust in the opposite direction. The collective effect of billions upon billions of these photons was a constant, very slight push toward the Sun, exactly matching the observed anomalous deceleration. It was a thermal recoil force, a subtle engineering effect that had not been fully accounted for in the original trajectory models. While the thermal explanation is now widely accepted as the primary cause of the Pioneer Anomaly, it's fascinating to note that the story may not be entirely closed. Some researchers point out that after accounting for the thermal effect, a tiny, residual anomaly might still linger in the data, a discrepancy so small it could be a statistical fluke or an unmodeled systematic error. But its legacy is secure. The decades-long investigation into this tiny drift serves as a powerful lesson in scientific rigor. It demonstrates how even the most exciting possibilities, new physics, dark matter, modified gravity, must bow to the relentless pursuit of a conventional explanation. It shows that our deepest understanding of the cosmos is built not just on grand theories, but on the painstaking accuracy of our measurements and our models. The Pioneer Anomaly reminds us that the universe's secrets are not always hidden in distant quasars or dark energy. Sometimes they are encoded in the silent, patient flight of a human-made object, a testament to how the smallest, most meticulous details can force us to re-examine our place in the cosmos. Far beyond the orbit of Neptune, in the cold, perpetual twilight of the outer solar system, lies a vast frontier of icy worlds. This is the Kuiper belt, a sprawling disk of frozen remnants left over from the planet-building era, often described as a distant, oversized cousin to the asteroid belt. For years, astronomers have been meticulously mapping this region, expecting to find a sea of objects that gradually thins out as you travel further from the Sun, fading slowly into the emptiness of interstellar space. But the universe, it seems, has a habit of defying our simplest expectations. Instead of a gentle fade, the census of Kuiper belt objects reveals something far more puzzling. A dramatic and sudden drop in population at a distance of about 50 astronomical units from the Sun. It's as if this cosmic reservoir of ice and rock has run into an invisible wall, a boundary so sharp and unexpected that it has been named the Kuiper Cliff. This abrupt edge presents a significant challenge to our models of how the solar system formed. The prevailing theory suggests that the protoplanetary disk, the swirling cloud of gas and dust from which the planets coalesced, extended much further out. If that were the case, we would expect to see a steady distribution of icy bodies that becomes sparser and sparser with distance, not a precipitous cliff. Astronomers who have spent their careers peering into this distant realm express a sense of bewilderment. The data clearly shows a steep decline that is difficult to explain through natural processes of gradual depletion. It's like walking along a beach and finding that the sand doesn't gradually give way to deeper water, but instead you simply step off a sheer edge into an abyss. This cliff hints that the history of our solar system's outer reaches is far more complex and dynamic than we ever imagined. One of the most compelling and controversial explanations for this sharp boundary involves the gravitational hand of an unseen world. The hypothesis suggests that a planet-sized object, perhaps with a mass several times that of Earth, could be orbiting the Sun far beyond the Kuiper belt. This hypothetical world, often referred to as Planet 9 or Planet X, would not be gently influencing the orbits of these distant bodies. It could be acting as a gravitational shepherd. Its immense pull might be clearing out a zone, either by ejecting objects from that region entirely or by herding them into orbits that keep them from venturing closer to the Sun, thereby creating a stark inner edge to a more distant, yet-to-be-discovered population of objects. The gravitational signature required to create such a clean break is precisely the kind of clue that drives the hunt for this potential hidden planet. However, not all scientists are convinced that a hidden giant is the only answer. An alternative, and perhaps more straightforward, explanation is that the original protoplanetary disk from which our solar system formed genuinely did have a relatively sharp outer edge. The processes that led to the formation of the giant planets may have effectively truncated the disk, perhaps through gravitational interactions that stripped away material beyond a certain point, or because the cloud of material itself simply ended there. In this scenario, the Kuiper Cliff isn't a mystery to be solved, but a fossilized relic of the solar system's birth, a permanent scar showing us the original boundaries of the planetary construction zone. The challenge is that both theories, the unseen planet and the primordial edge, make specific predictions about what we should find even further out, predictions that are incredibly difficult to test. The primary obstacle to solving this mystery is the sheer difficulty of observing anything at such extreme distances. An object at 50 astronomical units receives only a tiny fraction of the sunlight that reaches Earth, making it extraordinarily faint. Detecting these icy worlds is like trying to spot a lump of coal in the deep ocean using only a single, dim flashlight. Surveys that have mapped the Kuiper Cliff have required the most sensitive telescopes and painstakingly long exposure times, and even then, they can only see the very largest objects. There could be a vast population of smaller, undiscovered bodies beyond the cliff that simply elude our current technology. Each new, more powerful telescope that comes online, like the Vera C. Rubin Observatory, brings with it the hope that we might finally peer beyond this boundary and see what, if anything, lies in the darkness on the other side. The existence of the Kuiper Cliff forces us to confront the limits of our knowledge about our own cosmic backyard. If such a prominent feature can remain unexplained right on our doorstep, what other boundaries and structures are waiting to be discovered in the even more remote Oort cloud, the spherical shell of icy bodies that is thought to envelop the entire solar system? This cliff is more than just a curious statistical anomaly. It is a clue pointing to a dramatic chapter in our solar system's early history, a time of gravitational upheavals and planetary migrations. It reminds us that the architecture of our celestial neighborhood may still hold secrets of monumental proportions, perhaps even the presence of a hidden world whose discovery would rewrite the maps of the sun's dominion. Just as we were mapping the outer boundaries of our own solar system and its mysterious Kuiper cliff, the universe delivered a visitor that made every map we had instantly feel local and provincial. In October 2017, astronomers at the University of Hawaii's Pan-STARRS-1 telescope detected a faint point of light moving against the backdrop of stars. At first, it was catalogued as just another small asteroid or comet, but as they tracked its path over the following days, something became startlingly clear. This object was moving far too fast to be bound by the sun's gravity. Its trajectory was not a closed ellipse but an open-ended hyperbola. It was not from here. It was a traveler from the vast space between the stars, the first object ever observed to have an interstellar origin. In a moment of profound significance, it was given a name, Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The excitement of this historic discovery was immediately tempered by profound puzzles. As telescopes around the world swiveled to observe our interstellar guest, they revealed a string of anomalies. The first was its shape. By measuring how its brightness changed dramatically over a period of hours, astronomers deduced that Oumuamua was not a roughly spherical object. Instead, it was tumbling end over end, and its light curve suggested an extreme, elongated shape. The best fit was an object at least 5 to 10 times longer than it was wide, resembling a cigar or a pancake tumbling through space. This was unlike any asteroid or comet seen in our own solar system. The second, and even more baffling, mystery was its motion. As Oumuamua sped away from the sun after its closest approach, a team led by astronomer Marco Micheli analyzed its trajectory with exquisite precision. They found that it was not following a path dictated by gravity alone. There was an extra push, a tiny but undeniable non-gravitational acceleration. It was speeding up as if propelled by an unseen force. This unexpected acceleration launched a fierce and fascinating scientific debate that continues to this day. The most common explanation for such behavior in a solar system object is outgassing. When a comet approaches the sun, its ices heat up and turn to gas, jetting off the surface and acting like a natural rocket engine. The problem was, Oumuamua showed no visible signs of outgassing. No cloud of gas and dust or coma surrounded it. No tail of material streamed behind it. It was dark and inert, so one hypothesis proposed that it was a peculiar kind of comet after all. Perhaps one whose outgassing was composed primarily of pure hydrogen or water vapor that was difficult to detect, and that the released dust was made of unusually large grains that didn't reflect much light. This could explain the acceleration without a visible coma, but it requires a very specific and unusual composition. Another compelling idea is that Oumuamua was not a comet, but a fragment of a larger body. Imagine a Pluto-like world orbiting another star. A collision or a close gravitational encounter could have torn a chunk from its surface, a shard of nitrogen ice that was sent flying into interstellar space. As this nitrogen iceberg approached our sun, the intense heat would have caused it to sublimate, much like a comet, but nitrogen ice vaporizes cleanly without producing the dusty debris that creates a bright tail. This theory neatly accounts for both the acceleration and the lack of visible outgassing, painting a picture of Oumuamua as a relic from the icy outskirts of a distant planetary system. Then there is the most controversial and certainly the most captivating hypothesis. The non-gravitational acceleration was remarkably similar to the effect of radiation pressure from sunlight. For a solar sail, a thin, lightweight structure designed to be pushed by light itself, this is exactly how it would behave. Could Oumuamua have been a piece of discarded alien technology, a derelict light sail from an advanced civilization? This idea, proposed by Harvard astronomer Avi Loeb, was met with intense skepticism from the broader scientific community, who argued that an extraordinary claim requires extraordinary evidence. The primary counter-argument is that we should always seek a natural explanation before invoking an artificial one. Yet, Loeb's point was that we should not dismiss the possibility simply because it is startling. We must let the data guide us, and in this case, the data did not perfectly fit any well-known natural model. The light sail hypothesis, while a long shot, forces us to confront the possibility that we might one day find evidence of other intelligence, not in a radio signal, but in the physical artifacts drifting between the stars. Each of these explanations has its strengths and its weaknesses. The comet theory is simple but requires Oumuamua to be an oddity we've never seen before. The nitrogen iceberg idea is elegant but speculative, as we have no direct evidence of such objects. The light sail hypothesis is the most dramatic but remains the least likely, a possibility of last resort. The frustrating truth is that Oumuamua is now too far away and too faint to ever be observed again. It has receded back into the interstellar dark, taking its secrets with it. We are left with a single, fleeting data point, a blurry photograph of a cosmic stranger that passed through our neighborhood for a few short weeks. This brief encounter forces a profound reflection. Oumuamua was not aiming for us, our solar system was simply in its way. Its visit was a matter of chance, but if one interstellar object passed through in just a few years, we've had the capability to detect such things, then the galaxy must be teeming with them. Thousands, perhaps millions, of such travelers could be passing through the solar system at any given moment, most too small or too dark for us to ever notice. Oumuamua was our first glimpse into the vast population of material that must be sailing between the stars, the cosmic flotsam and jetsam ejected from countless other planetary systems. Its passage, while brief, opened an entirely new field of astronomy, one dedicated to studying these interstellar nomads. It taught us that our solar system is not an isolated island, but part of a dynamic, interconnected galaxy where even the emptiness is filled with visitors. While the strange journey of Oumuamua reminds us of the dynamic nature of our galactic neighborhood, it also highlights the incredible stability that has characterized our own planet for billions of years, a stability that itself presents a profound scientific puzzle. Consider the fundamental engine of our solar system, the Sun. We know that stars like our Sun grow steadily brighter as they age, burning through their hydrogen fuel. This leads to a startling contradiction. If we rewind the clock by 3 or 4 billion years, our Sun was about 30% dimmer than it is today. According to our basic understanding of climate physics, a weaker Sun should have meant a much colder Earth. In fact, climate models suggest that with the Sun's output that low, the entire planet should have been a global snowball, a frozen world locked in ice from pole to pole. Yet the geological record tells a completely different story. Ancient rocks from that very period, some of the oldest on Earth, show clear evidence of having been formed in the presence of liquid water. Ripples preserved in stone, deposits from flowing rivers, and minerals that can only form in warm water all point to an Earth that was not only ice-free, but also hospitable enough for the first life forms to emerge and thrive. This glaring inconsistency between the cold reality dictated by astrophysics and the warm, wet world revealed by geology is the faint young sun paradox, and it has been a central challenge for climatologists and planetary scientists for decades. As one prominent climate scientist put it, the evidence for liquid water is unequivocal. The problem isn't with the rocks, it's with our models. We are clearly missing a crucial piece of the puzzle that kept the early Earth warm. This paradox forces us to ask what powerful insulating blanket could have wrapped our planet, trapping enough of the sun's meager heat to prevent a global glaciation. The most widely investigated solution points to the composition of Earth's ancient atmosphere. Today, we worry about the greenhouse effect from carbon dioxide, but in the distant past, the atmosphere may have been filled with far higher concentrations of greenhouse gases. Think of carbon dioxide and methane as a planetary winter coat. If the early atmosphere contained tens or even hundreds of times more carbon dioxide than it does today, the resulting greenhouse effect could have easily compensated for the fainter sun. This high level of carbon dioxide could have been sustained by intense volcanic activity, which was much more common on the young, geologically active Earth, constantly replenishing the atmosphere with the gas. Another compelling possibility involves a different greenhouse gas, methane, produced by early forms of life such as methanogens. Methane is a far more potent greenhouse gas than carbon dioxide, molecule for molecule. A relatively small amount of methane in the atmosphere, perhaps along with ammonia, could have provided a powerful warming effect. This introduces a fascinating feedback loop. A warmer planet allowed life to flourish, and that life, in turn, produced gases that maintained the warmth. However, this theory has its complications, as methane is fragile and can be broken down by ultraviolet light without a protective ozone layer, which didn't exist yet. This has led some researchers to propose a haze of organic particles in the atmosphere, similar to that seen on Saturn's moon Titan, which could have acted as a shield protecting the methane and contributing to the warming in complex ways. Beyond the atmosphere itself, the planet's reflectivity, or albedo, plays a critical role. A brighter, more reflective surface bounces more sunlight back into space, leading to cooling. Our modern Earth has highly reflective ice caps and clouds. The early Earth, however, may have been significantly darker. With less landmass exposed, the continents were still forming. The planet would have been dominated by dark ocean water, which absorbs heat efficiently. Furthermore, the lack of land-based, reflective vegetation and potentially different cloud cover patterns could have resulted in a much lower overall albedo. This darker planet would have absorbed a greater percentage of the sun's precious, albeit fainter, light, converting it into heat and helping to keep the oceans liquid. The interplay between atmospheric composition and surface reflectivity likely created a delicate balance that maintained a stable climate for hundreds of millions of years. Resolving this paradox is about far more than just understanding our own past. It is absolutely crucial for the search for life beyond Earth. When we look at distant exoplanets orbiting other stars, one of the key factors we consider is whether they lie in the habitable zone, the region where temperatures might allow for liquid water. The faint young sun paradox teaches us that the habitable zone is not a fixed distance. It is a dynamic concept that depends heavily on the planet's atmosphere and surface conditions. A planet with a thick, greenhouse-rich atmosphere could be habitable much further from its star, while a planet with a thin atmosphere or a highly reflective surface might need to be much closer. It shows that a planet's biology and geology can actively work to maintain its own habitability, a concept known as the Gaia hypothesis. This understanding expands our vision of where life could potentially arise, suggesting that even planets around dimmer stars might harbor conditions suitable for life if their atmospheric chemistry is just right. This entire line of inquiry forces a deeply reflective question. We exist on a planet that, against the odds, remained balmy and stable for billions of years, allowing life to evolve from single-celled organisms to a civilization that can ponder its own origins. How many of these factors were mere chance, and how many are the inevitable result of planetary processes? Was Earth's climate stability a fragile, unlikely miracle, or is it a common outcome for rocky planets with water and active geology? The faint young sun paradox connects the long-term evolution of our star directly to the story of life itself, revealing that our existence is the product of a complex and finely tuned interplay between the cosmos above and the dynamic world below. This delicate balance on our own planet naturally leads us to wonder if our position in the galaxy at large might also play a special role in fostering such a long-lived, stable environment. So we've seen how the delicate balance of our own atmosphere helped Earth defy the faint young sun. But what about our position in the galaxy itself? Is our solar system's location just as crucial? The idea that not all neighborhoods in a vast city are equally safe or desirable extends to an entire galaxy. Our Milky Way is a sprawling metropolis of stars, but it's not a uniform expanse of habitable real estate. Astrobiologists have developed the compelling concept of the galactic habitable zone, a theoretical region where conditions are just right for complex life to arise and, more importantly, to persist long enough to evolve into something interesting. It's a cosmic sweet spot, and our solar system appears to be sitting right in the middle of it. Venture too close to the bustling downtown of the galactic center, and the environment becomes lethally hostile. The density of stars in the inner regions of the Milky Way is immense. While this might seem like a vibrant community, it's a dangerous one. A nearby supernova, the explosive death of a massive star, would be a catastrophic event for any nearby planetary system. The blast of radiation and high-energy particles could strip away a planet's ozone layer, bathing its surface in deadly ultraviolet radiation from its own star, effectively sterilizing the world. Gamma-ray bursts, those unimaginably powerful cosmic explosions we discussed earlier, are also thought to be more common in star-forming regions, which are more frequent in the inner galaxy. Life in such a neighborhood would be living under a constant threat of extinction-level events, making the long-term stability required for the evolution of intelligence incredibly unlikely. On the other hand, if you travel too far out into the galactic suburbs towards the sparse outer rim, you encounter a different problem, a poverty of resources. The universe began with only hydrogen and helium, all the heavier elements essential for life as we know it: the carbon, oxygen, nitrogen, iron, and silicon that make up rocky planets and living organisms, were forged in the hearts of stars and scattered by their explosive deaths. This process of chemical enrichment is most concentrated in the inner and central regions of the galaxy. In the far outskirts, the abundance of these vital heavy elements drops off significantly. A planetary system forming out there might struggle to assemble rocky, Earth-like planets at all, instead creating worlds dominated by ice and gas. Without a rocky planet with a protective magnetic field and active geology, the chances for life diminish dramatically. It's like trying to build an advanced technological civilization on a world without the necessary raw materials. This leads to an active debate among scientists. Just how wide is this galactic habitable zone, and is our location truly a prerequisite? Some models suggest it might be a relatively narrow ring, perhaps encompassing only between 5 and 10% of the stars in a galaxy like our own. Others propose a more optimistic view, arguing that the zone could be much broader, especially if life proves to be more resilient than we anticipate. A key factor in this equation is our specific position, not just in the zone, but within the structure of the galaxy itself. Our solar system resides in what's known as the local bubble, a region of relatively low-density interstellar gas, and we are currently passing through a quiet spur between the larger spiral arms of the Milky Way. Spiral arms are beautiful to look at, but they are turbulent places packed with dense molecular clouds and bright, short-lived massive stars. Our orbit around the galactic center is remarkably circular, keeping us at a stable distance from the core and minimizing the number of times we plunge through these chaotic and dangerous spiral arms. This orbital stability has granted our planet hundreds of millions of years of relative peace, uninterrupted by nearby stellar cataclysms, providing the extended period of environmental stability that complex evolution demands. So, when we step back and consider our place in the cosmos, we find ourselves in a remarkably privileged location. We are far enough from the galactic center to avoid the constant barrage of radiation, yet close enough to have been seeded with the necessary heavy elements for planet building. We are nestled in a quiet stellar neighborhood on a stable orbit that avoids the galaxy's most violent districts. This realization forces us to ask a profound question. Is our situation a rare cosmic fluke, or are there millions of other worlds orbiting their stars in similar galactic sweet spots? The sheer number of stars in the Milky Way, even within a narrow habitable zone, suggests the potential for many suitable abodes. Yet, the galactic habitable zone is just one layer of a much deeper puzzle, a filter that narrows the field of potential life-bearing worlds. It sets the stage, but it doesn't guarantee a performance. The next great mystery forces us to take a complete inventory of the cosmos, and in doing so, we've discovered that a shocking amount of the most basic stuff of reality seems to be missing. We have contemplated our special place in the galaxy, a seemingly privileged location that may have been key to fostering life. But this entire discussion is built upon a fundamental assumption that we know what our galaxy, and indeed the entire universe, is actually made of. We talk about stars, planets, and gas, the ordinary stuff of atoms. Yet, when cosmologists perform a complete cosmic inventory, they are confronted by a deeply embarrassing problem. About half of all the ordinary matter, the protons, neutrons, and electrons that constitute every star, every planet, and every one of us, is simply missing. This is not the mysterious dark matter or dark energy. This is the familiar baryonic matter, the stuff we are made of, and we can't find about 50% of it anywhere. This glaring discrepancy is known as the missing Baryon problem, and it represents a major hole in our understanding of the universe's most basic composition. The case for this missing matter begins with our most precise snapshot of the infant universe, the cosmic microwave background. The subtle fluctuations in this afterglow radiation act as a cosmic ledger, recording the total amount of baryonic matter present just 400,000 years after the Big Bang. By analyzing these patterns, cosmologists can state with great confidence how much ordinary matter the universe started with. As one researcher working with Planck satellite data explained, the CMB gives us a budget. It tells us exactly how much baryonic matter was in the universe at that very early time. The laws of physics tell us that matter cannot be created or destroyed, so that budget should still be valid today. When we then add up all the ordinary matter we can directly see, all the stars shining in all the galaxies, all the cold gas in and around them, and all the dust, we come up dramatically short. It's as if you had a detailed receipt for $100 worth of groceries, but when you unpack the bags at home, you only find about $50 worth of food. The question is, where is the rest? The leading suspect in this cosmic case is not lurking in some distant, unseen galaxy. Instead, it is believed to be hiding in the vast, empty spaces between the galaxies themselves, in a form known as the warm-hot intergalactic medium, or WHIM. Picture the cosmic web we discussed earlier, with its great filaments of dark matter and galaxies. Theorists predict that the gravitational pull of this web has been slowly gathering the ordinary matter, the gas that didn't collapse into galaxies, and heating it to immense temperatures between 100,000 and 10 million degrees Kelvin. At these temperatures, the gas becomes a thin, ionized plasma, so diffuse that it emits very little light and is virtually invisible to our telescopes. It's not dark matter, it's brilliantly hot, ordinary matter that is simply too spread out to see easily. This WHIM is thought to be the repository for the missing baryons, woven into the architecture of the universe itself. The immense challenge, then, is detecting this ghostly plasma. How do you find something that is both incredibly hot and incredibly thin, filling the voids between galaxies? Astronomers have had to become cosmic detectives, using indirect methods to spot its shadow. The primary technique involves using the brightest beacons in the universe, quasars. As the intense light from a distant quasar travels across billions of light years to reach us, it passes through these filaments of the WHIM. The hot gas in the WHIM doesn't block the light entirely, but it does absorb specific wavelengths, imprinting a unique fingerprint on the quasar's spectrum. It's like looking at a brilliant lighthouse through a faint, hot fog. The fog doesn't extinguish the light, but it leaves a specific stain on the beam that tells you about the fog's composition. By painstakingly analyzing the light from many quasars, astronomers have begun to find these absorption lines, these telltale signatures of highly ionized oxygen and other elements, confirming that the WHIM does indeed exist and contains a significant amount of mass. However, the task is monumentally difficult. The signals are exceedingly weak, and they require the most sensitive space-based telescopes, like the Hubble and the Chandra X-ray Observatory, to detect. Furthermore, because the gas is so diffuse, you need to look through a very long path length to see enough of it to get a measurable signal. This is like trying to detect a specific type of gas in the Earth's atmosphere by looking through just a few feet of air. You might not see anything. But if you look through miles of atmosphere, the signal becomes stronger. Astronomers are effectively looking through millions of light years of the WHIM to find these faint fingerprints. Recent observations have indeed begun to account for a large portion of the missing baryons, suggesting that the solution to this decades-old puzzle is within reach, hidden in the delicate patterns of light from the most distant objects in the cosmos. This entire investigation forces a humbling realization. We have spent centuries mapping the bright, obvious structures of the universe, the galaxies and stars, only to discover that half of the normal matter was hiding in the shadows all along, in the seemingly empty spaces between everything. It begs a broader question. If something as fundamental as the atoms of the universe can evade our detection for so long, what other components of reality are we still missing? Are there other forms of matter or energy, even more subtle than the WHIM, that remain completely unknown to us? Solving the missing baryon problem is not just about balancing a cosmic ledger. It is about completing our basic inventory of the universe, confirming that we truly understand what the cosmos is made of, from the brightest quasar to the most desolate void. This quest to see the invisible in the voids takes us to our next mystery, one that challenges the very principle that the universe should look the same in every direction. After grappling with the missing pieces of our own cosmic inventory, we turn to what should be the most impartial map of all, the afterglow of creation itself. The cosmic microwave background radiation is the oldest light we can see, a snapshot of the universe when it was a mere 400,000 years old, a fading echo of the Big Bang. It is the most perfect blackbody radiation known to science, a testament to the uniformity of the early cosmos, with a temperature that varies across the sky by less than 1/1000th of a degree. These tiny fluctuations, these faint ripples in temperature, are the seeds from which all the structure in the universe, the galaxies, the clusters, the vast cosmic web, would eventually grow. They are the blueprint for everything we see, but when cosmologists began to analyze this blueprint in exquisite detail, using satellites like Oumuamua and Planck, they discovered something deeply unsettling. The map of the early universe appears to have a preferred direction, an alignment that seems to point, bizarrely, towards us. This strange and controversial pattern has been dramatically nicknamed the axis of evil, and it threatens one of the most cherished principles in all of cosmology. The foundational assumption upon which modern cosmology is built is the cosmological principle. This principle states that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means that matter is evenly distributed. No one large region is significantly different from any other. Isotropic is an even more profound assertion. It means the universe looks the same in every direction. There is no center, no edge, and no preferred orientation. The laws of physics are the same everywhere. The axis of evil anomaly directly challenges the isotropic part of this principle. When scientists decompose the CMB map into its constituent patterns, much like separating a complex musical chord into its individual notes, they find that the largest scale fluctuations, the biggest ripples in the primordial sea, are not randomly oriented. Instead, they appear to be aligned along a particular axis that correlates unnervingly with the plane of our own solar system and the direction of our galaxy's rotation. It is as if the universe's earliest fingerprint has a marking that lines up with our local celestial neighborhood, a correlation that should be statistically impossible if the cosmos is truly directionless. The scientists who first identified this pattern were deeply troubled by its implications. As one leading cosmologist involved in the Planck mission analysis remarked, "You work for years to build this perfect map of the early universe, and then you see something like this. Your first instinct is to assume you've made a mistake. You check the instrument, you check for contamination from our own galaxy, you check the data processing pipelines from every conceivable angle." The name Axis of Evil itself, coined half-jokingly by cosmologist Joe Megiddo, reflects the profound unease it causes. If this alignment is real and not an artifact of our measurements, it suggests that the universe has a fundamental orientation, a preferred direction that breaks the sacred rule of isotropy. This would mean that our location in the cosmos is not arbitrary. The largest patterns in creation have a mysterious connection to our own tiny corner of it. It would be a Copernican revolution in reverse, hinting that we might, in some bizarre way, be at the center of something after all. Of course, the most likely explanation for such a startling result is the simplest one: we are being fooled by our own perspective. Primary suspect is foreground contamination. Our view of the pristine CMB is filtered through the bustling environment of our own Milky Way galaxy. Dust, gas, and synchrotron radiation from electrons spiraling in magnetic fields can all emit microwaves that mimic or distort the primordial signal. Perhaps the intricate process of subtracting this galactic foreground has inadvertently left behind a residual pattern that looks like an alignment. Another possibility is that the anomaly is not in the universe, but in our method of analysis. The statistical techniques used to search for these alignments are incredibly complex, and it is possible that we are unconsciously biasing the results, finding patterns that we subconsciously expect to see, a phenomenon known as confirmation bias. The scientific community continues to scrutinize the data, with each new analysis and data release from missions like Planck providing a more refined, but still inconclusive picture. If, after all this scrutiny, the axis of evil persists, then we are forced to consider more exotic explanations that venture into the realm of new physics. Some theorists have proposed that this alignment could be a relic from a time before the Big Bang, an imprint from a pre-inflationary era when the universe's geometry was fundamentally different. Perhaps the universe is not perfectly isotropic on the very largest scales, and our observable universe is just one patch of a grander structure that does have a preferred orientation. Other, more mind-bending ideas involve the influence of other universes in a vast multiverse. Could the gravitational pull of a neighboring universe, brushing up against our own in a higher dimensional space, have left a tidal imprint on our CMB, a cosmic bruise that establishes a directional preference? These are highly speculative ideas, but they illustrate the profound shift in thinking that the axis of evil demands if it proves to be genuine. The controversy remains unresolved. For every paper that claims the anomaly is a significant detection, another argues that its statistical significance is low and that it will vanish with better data. It sits in an uncomfortable limbo, too persistent to ignore but not yet definitive enough to overturn our standard models. This forces us to confront a deeply philosophical question about the nature of our exploration. Are we, in our quest to understand the cosmos, capable of truly seeing it objectively? Or is our view forever filtered through the lens of our own existence, our local environment imposing its signature on the most distant signals we receive? The axis of evil is more than just a curious statistical fluke. It is a reminder that the universe may still hold surprises that challenge our most basic assumptions about reality, suggesting that the cosmic stage may have a hidden orientation we are only just beginning to perceive. The story of the Big Bang is a scientific triumph, a narrative pieced together from the faintest echoes of the universe's birth. One of its most compelling chapters is Big Bang nucleosynthesis, the process that forged the first atomic nuclei in the fiery opening minutes of existence. The calculations describing this brief, intense period are remarkably precise. By knowing the conditions of the early universe, its density, temperature, and expansion rate, physicists can predict with stunning accuracy how much of each light element should have been created. The observed abundances of hydrogen and helium, the two simplest elements, match the predictions almost perfectly. It is a resounding confirmation that our understanding of the universe's first moments is fundamentally correct. Yet, nestled within this success story is a single, stubborn anomaly, a tiny flaw in an otherwise perfect theory. For the third lightest element, lithium, the math simply does not add up. The universe, according to our best models, should contain about 3 times more lithium than we can actually find. This is the Lithium Problem, a small but profound discrepancy that has cosmologists and nuclear physicists scratching their heads. When scientists look for the primordial lithium, they search for it in the most ancient stars in our galaxy. These stellar relics, known as population 2 stars, formed from gas that was nearly pristine, contaminated only by the elemental ash from the Big Bang itself. By analyzing the light from these ancient suns, astronomers can measure the chemical composition of the early universe. Time and again, the results are the same. The amount of lithium-7, the most common isotope, is consistently about 1/3 of what the Big Bang models predict. As one leading nuclear cosmologist expressed with a mix of frustration and fascination, we have checked the nuclear reaction rates in our particle accelerators. We have refined the measurements of the cosmic microwave background to pin down the density of ordinary matter with exquisite precision. Every time we think we've found an error, the discrepancy remains. The universe seems to be hiding its lithium from us. This persistent puzzle has forced researchers to consider some truly exotic explanations. One possibility ventures into the realm of new physics, suggesting the existence of previously unknown particles that were present in the early universe. For instance, certain hypothetical particles could have interacted with normal matter in a way that altered the nuclear reactions, perhaps by decaying and injecting extra neutrons at a critical moment, which would have skewed the final balance of elements away from lithium production. Another equally speculative idea involves the concept of inhomogeneous nucleosynthesis. What if the early universe wasn't a perfectly smooth soup? What if it had lumps and variations in density? In such a scenario, nuclear fusion would have proceeded differently in different regions, potentially resulting in a lower overall yield of lithium. While intriguing, these ideas remain largely untested, stretching the boundaries of our known physics to solve a problem rooted in the most basic nuclear processes. Perhaps the solution is less about the Big Bang and more about what happened to the lithium afterward. Could the lithium have been destroyed rather than underproduced? Stars are immense nuclear furnaces, and their interiors are hostile environments. It is possible that the surfaces of these ancient stars, which is what we observe, do not reflect their internal composition. Complex processes like diffusion could have caused the lightweight lithium atoms to sink from the surface down into the hotter interior, where the intense temperatures would have torn them apart in nuclear reactions. Alternatively, these old stars might have been born with the predicted amount of lithium, but then encountered and consumed clouds of lithium poor gas later in their long lives, diluting the original signature. While these stellar astrophysics solutions are compelling, they require very specific conditions to work for every single ancient star we observe, which seems like a difficult coincidence. The true significance of the lithium problem lies not in its size but in its implications. Here we have a theory, Big Bang nucleosynthesis, that is spectacularly successful for 99% of the light elements. The fact that it fails for just one element and fails so consistently is a powerful reminder that even our most well-tested models may have hidden flaws. It is a tiny crack in the foundation of modern cosmology. This forces us to ask a humbling question. If we can be so confident about the origins of hydrogen and helium, yet so wrong about lithium, what other small errors are lurking in our understanding of the cosmos? Could other constants or processes be slightly different than we assume? Errors that are currently masked but could lead to major revelations about the nature of dark matter, dark energy, or the unification of physics. The lithium problem beautifully connects the largest scales of the cosmos, the entire universe in its first 3 minutes, to the smallest scales of atomic nuclei, proving that the quest to understand reality requires us to look carefully at both the grand tapestry and the tiniest mismatched threads. In the 1960s, astronomers were confronted with a puzzle that seemed to defy logic. While scanning the skies with radio telescopes, they detected point-like sources of intense radio waves. When they turned optical telescopes towards these coordinates, they saw what appeared to be faint blue stars, but there was something profoundly wrong with these so-called quasi-stellar radio sources, or quasars for short. Their light revealed an incredible redshift, a stretching of light waves that indicated they were not stars in our galaxy, but objects fleeing from us at tremendous speeds, placed at distances of billions of light years. The implication was staggering. To appear as bright as a nearby star from such an immense distance, these objects had to be emitting almost unimaginable amounts of energy. As one bewildered astronomer of the era put it, the idea that a single star-sized object could outshine an entire galaxy containing hundreds of billions of stars was at first almost laughable. It challenged the very foundations of what was thought to be possible. The resolution to this mystery was as elegant as it was dramatic. A quasar is not a star at all. It is the blazing heart of a distant galaxy, an active galactic nucleus operating at its most extreme. The power source is a supermassive black hole, a gravitational monster weighing millions or even billions of times the mass of our Sun. But a black hole alone is dark. Its power is unleashed only when it feeds. In a quasar, vast quantities of gas, dust, and even entire stars are drawn into an inexorable gravitational dance towards the event horizon. This material does not fall straight in. Instead, it spirals into a flattened, superheated structure called an accretion disk, whirling around the black hole at near light speeds. The immense friction and gravitational stresses within this disk heat the gas to temperatures of millions of degrees, causing it to glow with a ferocious intensity that can outshine the combined light of every star in its host galaxy. It is a cosmic hurricane, a maelstrom of matter converting mass into pure energy with an efficiency far greater than nuclear fusion. This incredible engine does more than just produce light. It can also generate colossal jets of material. Perpendicular to the accretion disk, powerful magnetic fields are thought to funnel some of the infalling matter into narrow beams, shooting it back out into space at relativistic velocities. These jets, which can extend for thousands of light years, are themselves brilliant sources of radio waves and other radiation. The combined effect is a lighthouse beacon of staggering power, visible across the observable universe. The reason we see quasars as point-like is that this entire energetic circus is confined to a region not much larger than our own solar system. To concentrate the energy of 100 galaxies into such a tiny volume is an almost incomprehensible feat of cosmic power, a testament to the ferocious appetite of supermassive black holes. This leads to a compelling mystery. What triggers such a period of intense activity? Why do some galaxies light up as quasars while others, like our own Milky Way, have quiet, dormant black holes? The answer seems to lie in the availability of fuel. A quasar phase is likely a temporary, albeit brilliant, stage in a galaxy's life. It may be triggered by a major galactic collision or merger, an event that funnels huge reservoirs of cold gas towards the central black hole, igniting the furnace. Another possibility is the instability of a large gas disk within the galaxy itself, which could suddenly drain towards the center. What is clear is that quasars were far more common in the early universe, a fact that paints a picture of a much more violent and chaotic cosmic era. Billions of years ago, galaxies were closer together, collisions were frequent, and gas was more plentiful, providing the perfect conditions for these cosmic powerhouses to flare into existence. This history forces a fascinating reflection on our own place in the cosmos. The supermassive black hole at the center of the Milky Way, Sagittarius a star, is quiet today, a sleeping giant. But was it always so? It is entirely possible that our own galaxy experienced a quasar phase in its distant past, a time when its central black hole was actively feeding, and its core shone with a brilliance that would have been visible from another galaxy. If that were the case, any hypothetical astronomer in that distant galaxy would have seen a brilliant point of light where our Milky Way now appears as a gentle spiral. The study of quasars is not just about understanding the most energetic objects in the universe. It is a window into the violent youth of all galaxies, including our own. It shows us that the serene beauty of a modern spiral galaxy like the Milky Way is the calm after a storm, a maturity that follows a period of brilliant, explosive growth. Imagine having two incredibly precise rulers, each crafted by different master scientists to measure the exact same distance. You use the first ruler and it gives you one answer. You then use the second, which is just as trusted and accurate, and it gives you a different, stubbornly inconsistent result. This is not a trivial discrepancy. It is a fundamental challenge to your understanding of measurement itself. This is precisely the situation cosmologists find themselves in today with the most important number in the universe, the Hubble constant, which measures the rate at which the cosmos is expanding. The Hubble tension is the name given to this perplexing and persistent disagreement between the two most reliable methods we have for pinning down this critical value, and it has become the most pressing puzzle in modern cosmology, a potential crack in the foundation of our understanding that could point toward entirely new physics. The first method acts as a local cosmic speed gun. Astronomers use a beautiful chain of cosmic milestones to build a distance ladder out into the nearby universe. It begins with Cepheid variable stars, which are stars that pulse with a regularity that is directly tied to their true brightness. By measuring their pulse rate, we know their intrinsic brightness, and by comparing that to how bright they appear from Earth, we can calculate their distance with remarkable accuracy. These Cepheids are used to calibrate the next rung on the ladder, Type 1, a supernova. These stellar explosions are even brighter, acting as standard candles that can be seen across much greater distances. By observing these supernovae in galaxies whose distances have been set by Cepheids, astronomers can measure how fast those galaxies are moving away from us, providing a direct measurement of the expansion rate in our cosmic neighborhood. This local measurement is incredibly robust, refined over decades of meticulous observation. The second method takes us back to the very beginning, using the cosmic microwave background as a fossilized snapshot of the infant universe. Satellites like Planck have mapped the faint whispers of this afterglow with exquisite detail. The tiny fluctuations in temperature and density seen in this map encode a vast amount of information about the composition and geometry of the early cosmos. By plugging these measurements into our standard model of cosmology, known as the lambda cold dark matter model, we can run the cosmic film in reverse, predicting how the universe should have evolved and expanded to arrive at the state we see today. This method gives us a prediction for what the Hubble constant should be, based on the conditions of the early universe. The problem, the heart of the tension, is that these two numbers do not agree. The local measurement suggests a faster expansion rate, while the early universe measurement predicts a slower one. The discrepancy is small in percentage terms, but it is far larger than the estimated margins of error for each method. As one leading cosmologist involved in the Planck mission has stated, this isn't just a statistical fluke. The error bars have shrunk to the point where they no longer overlap. We are faced with a real inconsistency. This is why the Hubble tension is described as a potential crisis. Our standard model of cosmology has been spectacularly successful, explaining everything from the abundance of light elements to the large-scale structure of the cosmos. It is the bedrock of modern astrophysics. If two of its most precise pillars are giving conflicting answers, it suggests that the model itself might be incomplete. This has ignited a fervent search for solutions which generally fall into two camps. The first possibility is that there is an unaccounted for systematic error in one of the measurements. Perhaps our understanding of Cepheid variables is subtly wrong, or maybe there is an unknown source of dust affecting the brightness of distant supernovae. Teams are now using the James Webb Space Telescope to cross-check the Hubble Space Telescope's measurements of Cepheids with unprecedented infrared clarity, hoping to eliminate any lingering observational biases. If the discrepancy holds as it seems determined to do, then we must venture into the realm of new physics. perhaps dark energy, the mysterious force driving the acceleration of the universe, is not constant as we have assumed. Maybe its strength has increased over time, which would cause the recent expansion to be faster than predicted from the early universe. Another compelling idea involves early dark energy, a new form of energy that may have briefly existed in the universe's first few 100,000 years, altering the sound waves imprinted on the cosmic microwave background, and thus throwing off the prediction from the early universe. Other theorists have proposed the existence of a new type of neutrino, often called sterile, because it would interact only gravitationally, which would change the rate at which structures formed in the early cosmos. There are even more exotic suggestions, like the idea that dark matter possesses some unknown interaction with itself or with radiation. The immense efforts to resolve this tension are a testament to its importance. The James Webb Space Telescope is not just looking at the first galaxies. It is also being used to tighten the measurements on the distance ladder, observing Cepheids in new wavelengths to see if that resolves the issue. Next-generation observatories like the Vera C, Rubin Observatory and the Nancy Grace Roman Space Telescope will discover thousands more supernovae, providing a statistical weight that will either cement the tension or finally reveal a hidden error. This is not an academic exercise, it is a direct test of our cosmic model. The Hubble tension forces us to confront a profound possibility. We might be on the verge of a major shift in our understanding, a moment where a small but stubborn discrepancy in a single number leads us to discover that our universe is even stranger and more wonderful than we had imagined, and that the laws we hold as constant may, in fact, be more dynamic than we ever dreamed. How will the grand story of the cosmos ultimately conclude? Will it be a final, fiery collapse, a slow, frozen fade, or an ending so strange it defies our current imagination? The ultimate fate of the universe is not just a question for philosophers. It is a scientific puzzle whose answer is written in the subtle interplay between two opposing forces, the outward push of dark energy and the inward pull of gravity. For much of the 20th century, cosmologists debated between two classical scenarios. The first, known as the Big Crunch, envisioned a universe where the collective gravity of all matter eventually overcame the expansion, pulling everything back together in a dramatic reversal of the Big Bang. Galaxies would rush towards each other, the cosmic background radiation would heat up until it glowed visible, and all structure would be compressed into an ultra-hot, ultra-dense singularity, a cosmic cycle ending where it began. The alternative was a more gradual but no less final demise, the heat death or the big freeze. In this scenario, expansion continues forever, but gravity gradually slows it down to a near halt. Stars burn out, galaxies evaporate as their stars drift apart or fall into central black holes, and those black holes themselves eventually evaporate over trillions of years via Hawking radiation. The universe would approach a state of maximum entropy, a uniform, lukewarm sea of diluted particles and radiation where no more work can be done and no new structures can form. It would be an eternal, silent, and dark equilibrium. The discovery in the late 1990s that the universe's expansion is not slowing down but accelerating fundamentally shifted this debate. The relentless push of dark energy has led most cosmologists to strongly favor the heat death scenario, albeit with a terrifying twist. Because the expansion is accelerating, the universe won't just expand slowly forever. It will stretch apart at an ever-increasing rate. This doesn't just mean things get far apart. It means that the very fabric of connected space between bound structures will eventually be torn asunder. First, galaxy clusters will be isolated from one another. Then individual galaxies will be pulled apart. And in the far, far future, even solar systems and planets will be ripped from their gravitational moorings. The final stage of this accelerated heat death is so extreme that it has earned its own name, the Big Rip. In this speculative but plausible outcome, if the strength of dark energy increases over time, its repulsive force could become infinite. In a finite span of time, the acceleration would overcome the forces holding galaxies, stars, and even atoms together. First galaxies, then stars, then planets, and finally molecules and atoms would be violently torn apart in a final, catastrophic moment that would erase all structure from the cosmos. The ultimate fate hinges entirely on the precise nature of dark energy, whether it remains constant, weakens, or grows stronger, a question that remains one of the greatest unsolved problems in physics. Beyond these classical fates born from general relativity, quantum physics introduces even more speculative and arguably more frightening possibilities. One of the most dramatic is the concept of vacuum decay. Our universe may not be in the most stable state possible. Think of it like a valley, but not the lowest valley in the landscape of reality. Our current vacuum might be a false vacuum, stable for now, but potentially capable of decaying into a true vacuum with lower energy. This decay could be triggered randomly at any point in space and time. If it happened, a bubble of true vacuum would form and expand outward at the speed of light, rewriting the laws of physics as it goes. The fundamental constants that allow for atoms, molecules, and life itself would be permanently altered within the bubble. There would be no warning. One moment the universe would be as it is, and the next a wave of absolute annihilation would sweep through, obliterating reality as we know it and replacing it with something utterly alien and likely incapable of supporting any complex structure. It would be an end not with a whimper or a bang, but with a silent, instantaneous rewrite of the cosmic rulebook. This contemplation of finality inevitably leads us back to the idea of beginnings. Could the end of our universe simply be the start of another? The concept of a cyclical universe is a compelling alternative to a singular, linear timeline. Some cosmological models, such as conformal cyclic cosmology proposed by Roger Penrose, suggest that the ultimate heat death of one universe could, through a complex transformation, become the low-entropy Big Bang of the next. In this view, the universe undergoes an endless series of cycles, or eons, each beginning with a hot, dense bang and ending in an expansive, empty coldness that then gives birth to the next cycle. Other theories, like the ekpyrotic model, propose that our universe exists on a three-dimensional brane, floating in a higher dimensional space, and that the Big Bang was the result of a collision with another brane. These collisions could happen repeatedly, creating a cyclical pattern of birth, destruction, and rebirth. While these ideas are highly speculative and lack definitive evidence, they offer a profound alternative to the bleak finality of the heat death, suggesting that the cosmos itself might be immortal, even if every individual incarnation is not. Pondering these vast timelines stretching over googolls of years forces a deeply philosophical reflection. What is the meaning of our fleeting existence, of all our art, science, and love, in a universe whose ultimate destiny appears to be either eternal silence or total annihilation? Perhaps the meaning is not in the destination, but in the journey itself. The fact that the universe has given rise to conscious beings capable of understanding its story, from the first spark of the Big Bang to its potential final flicker, is itself a remarkable event. We are the universe's way of knowing itself, and for a brief moment in cosmic history, we are here to witness its grandeur and contemplate its mysteries. This search for understanding, this drive to look into the abyss and ask what comes next, may be the most meaningful response to a cosmos that offers no final answer. And this very act of looking toward the end naturally sparks a question about the nature of reality itself, leading us to wonder if our universe is truly alone, or if it is just one bubble in an infinite, bubbling multiverse. But if the ultimate fate of our cosmos points towards an eternal, silent emptiness, could it be that this is not the only story being told? What if our entire universe, with all its galaxies, stars, and the tapestry of physical laws that govern them, is merely a single bubble in a vast, frothing ocean of cosmic reality? This is the staggering proposition of the Multiverse Hypothesis, an idea that pushes the very boundaries of science into the realm of the almost unimaginable. It suggests that what we call the universe is just one tiny domain within a much grander, potentially infinite, meta-universe where the rules of physics themselves can vary from one pocket to the next. This isn't merely science fiction, it emerges as a natural, albeit controversial, consequence of our most advanced theories about the cosmos's beginning and its most fundamental structure. The concept gains significant traction from the theory of cosmic inflation, the idea that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. As physicist Brian Greene often explains, inflation, once started, may be eternal. The inflating space can spawn new inflating regions in a never-ending process, creating a vast fractal landscape of pocket universes, forever disconnected from one another. Within each of these bubbles, inflation ends, allowing for the formation of stars and galaxies, but the fundamental constants of nature, the strength of gravity, the mass of an electron, the value of the cosmological constant could have settled into different, random values. In this Level 2 multiverse, as proposed by Max Tegmark, the reality we observe is simply the one where the numbers turned out to be right for our existence. The seemingly miraculous fine-tuning of these constants, which allows for atoms, chemistry, and life, is no longer a miracle, it's a selection effect. With an infinite number of universes, every possible combination of physical parameters will be realized somewhere. We, by definition, can only exist in one of the universes capable of supporting us. This idea extends even further into the esoteric realm of string theory, which attempts to unify gravity with quantum mechanics. String theory suggests that the fundamental building blocks of reality are tiny, vibrating strings, and the properties of particles are determined by how these strings vibrate. However, the mathematics of string theory allows for a colossal number of possible stable configurations, perhaps 10 to the power of 500 or more. Each of these vacua corresponds to a universe with a different set of physical laws and constants. This landscape of possibilities provides a potential physical mechanism for the multiverse. Our universe would simply be one valley in this unimaginably vast landscape, a single solution among a near infinity of others. In this view, the Big Bang was not a unique event, but the nucleation of our particular bubble from a higher dimensional quantum foam where countless other bangs are constantly happening. The multiverse hypothesis is often categorized into different levels, each more mind-bending than the last. The Level 1 multiverse is almost trivial. It's simply the space beyond our cosmic horizon. Since the universe is infinite and uniform, there must be regions so far away that their light has never had time to reach us. In those regions, every possible configuration of matter will be repeated. There is, statistically, another Earth with a person just like you reading this very sentence, separated from us by an unbridgeable distance. The Level 2 multiverse, driven by eternal inflation, introduces universes with different physical constants. Then there is the Level 3 multiverse, which arises from the many worlds interpretation of quantum mechanics. In this view, every time a quantum event has multiple possible outcomes, the entire universe splits, realizing all possibilities in branching, non-communicating timelines. Finally, the Level 4 multiverse encompasses all mathematically possible structures, suggesting that every universe that can be described by a consistent set of mathematical equations actually exists physically somewhere. Despite its compelling explanatory power for the fine-tuning problem, the multiverse faces a formidable and fundamental criticism: is it even science? The primary charge against it is testability. If these other universes are permanently beyond our observational reach, causally disconnected from our own, then how can we ever gather evidence to confirm or refute their existence? A theory that cannot be falsified by any conceivable experiment risks falling into the realm of metaphysics or philosophy. Prominent critics argue that invoking a near-infinite number of unobservable universes to explain the peculiarities of our own is a cop-out, a way to avoid finding a deeper, more elegant explanation that operates within our own cosmic domain. They worry that it could mark a retreat from the core principle of empirical science. Proponents counter that indirect evidence might still be found. Just as we can deduce the existence of a hidden object by its gravitational pull, we might find signatures of a multiverse imprinted on our own universe. Some have suggested that a collision between our universe and a neighboring bubble in the multiverse could have left a bruise on the cosmic microwave background, an unusual pattern of temperature variations like the controversial cold spot we discussed earlier. While no such definitive evidence has been found, the search continues, pushing the limits of our observational capabilities. The debate ultimately forces us to contemplate a profound possibility. If an infinite number of realities do exist, then somewhere, every possible version of history is playing out. Every choice you didn't make, every chance event that went another way, is real in some other branch of the cosmic tree. This idea stretches the imagination to its breaking point, blurring the line between the frontiers of theoretical physics and the deepest questions of philosophy and meaning, challenging us to wonder if our reality is just one page in an infinite library of existence. At the very heart of physics lies a sacred principle, a rule so fundamental it underpins our entire understanding of reality: information cannot be destroyed. Think of it this way: if you were to burn a book, the paper and ink would turn to ash and smoke. To all appearances, the information, the story, the words, the meaning seems lost. But in principle, if you could somehow collect every single atom of ash and every molecule of smoke, tracing their paths with perfect precision, you could theoretically reverse the process and reconstruct the book. The information was never truly gone. It was merely scrambled, transformed into a different, more chaotic state. This principle of the conservation of information is a cornerstone of quantum mechanics, essential for predicting the future from the past. Yet, there exists a place in the universe where this rule seems to be blatantly broken, a place where information appears to vanish without a trace, plunging into an abyss from which nothing, not even light, can return. This is the black hole information paradox, a profound conflict between the two great pillars of modern physics that has been raging for decades. The paradox was thrust into the spotlight by one of the most brilliant minds of our time, Stephen Hawking. In the 1970s, Hawking applied quantum theory to the edge of a black hole, the event horizon, and made a startling discovery. He realized that black holes are not completely black. Due to weird quantum fluctuations near the horizon, pairs of virtual particles can pop into existence. Normally, these particle-antiparticle pairs would annihilate each other almost instantly. But at the edge of a black hole, one particle can fall in while the other escapes, stealing a tiny amount of the black hole's energy in the process. This stream of escaping particles is what we call Hawking radiation. The devastating implication Hawking drew was that this radiation is entirely random or thermal. It carries no information about what fell into the black hole. As the black hole slowly evaporates over eons, it eventually vanishes completely. And if the Hawking radiation is featureless, then all the information about every star, planet, or book that ever fell in is irretrievably lost from the universe. The cosmic ledger has been permanently erased. As Hawking famously declared, it's not just that we can't retrieve the information, it is truly gone, a violation of quantum law. This conclusion sparked what physicists jokingly called the Black Hole War, a fierce and deeply philosophical debate primarily between Stephen Hawking and Leonard Susskind. Susskind and others argued vehemently that information cannot be lost. To allow it would mean that the universe is fundamentally unpredictable, that the same initial conditions could lead to different outcomes, unraveling the very fabric of quantum mechanics. Susskind championed the idea that information must be preserved, even if we don't yet understand how. The debate was not just academic, it was a battle for the soul of physics. The conflict reached a kind of resolution, or at least a truce, in 2004 when Hawking, in a dramatic reversal, conceded the argument. He admitted that information must somehow be preserved, stating that he had found a mechanism whereby information could escape a black hole, and even awarding a bet he had made on the subject. But how it escapes remained the central mystery. The most compelling modern solution to this puzzle is as beautiful as it is bizarre: the holographic principle. This idea suggests that all the information about what falls into a three-dimensional black hole is not lost inside its volume. Instead, it is encoded on its two-dimensional surface, the event horizon, like a cosmic piece of holographic film. In a hologram, a two-dimensional surface contains all the information needed to project a three-dimensional image. Similarly, the holographic principle posits that the universe itself might work this way, with the information about a volume of space being stored on its boundary. For a black hole, this means that every particle that crosses the horizon leaves an imprint, a tiny pixel of information on the surface. Then, as the black hole emits Hawking radiation, this process is not random. The radiation interacts with this encoded information on the horizon, subtly imprinting the data of what fell in onto the outgoing particles. It's an incredibly complex and slow process, like trying to scan and transmit the entire Library of Congress using a flickering candle. But in principle, the information is carried back out into the universe, preserved in the correlations between the Hawking radiation particles. Understanding this paradox is far more than an intellectual exercise. It is widely seen as the key to unlocking a theory of quantum gravity, the long-sought-after framework that would seamlessly unite Einstein's theory of general relativity with the quantum world. The paradox forces us to confront what happens where both theories are pushed to their limits, at the singularity of a black hole. Resolving it likely requires a fundamental revision of our concepts of space and time. Ideas like holography suggest that space-time itself may be an emergent property, a derivative of quantum information, rather than the fundamental stage upon which physics plays out. This leads to a question that pushes the boundaries of both science and philosophy. When an object, say, an astronaut, falls into a black hole, what truly happens to their identity? According to general relativity, they would pass through the event horizon and be stretched and crushed into the singularity. But if the holographic principle is correct, their information is instantly smeared across the horizon, a frozen, encoded shell from which their story is slowly radiated back out over billions of years. The paradox forces us to ask whether identity and information are one and the same, and what it really means for something to exist in a universe where the rules of location and reality itself may be nothing more than a complex illusion. After exploring the intricate filaments and dense clusters of the cosmic web, we must now turn our attention to the other side of this grand architecture, the immense silent voids that make up the bulk of the universe's volume. If the cosmic web is a sprawling metropolis of galaxies, then these voids are the continent-spanning deserts, regions of profound emptiness that challenge our understanding of how the universe organized itself. Among these, one stands out for its staggering scale and mystery: the Boötes Void, discovered in the 1980s by astronomers Robert Kirshner and his colleagues. This region of space is so exceptionally empty that it was initially dubbed a supervoid. Stretching across a diameter of approximately 250 million light-years, it is a spherical near-nothingness so vast that if you placed our Milky Way galaxy at its center, the nearest edge would be over 100 million light-years away. To put that in perspective, light traveling at 300,000 kilometers per second would take 250 million years just to cross from one side to the other. In a universe we believe is governed by gravity, a force that pulls matter together, the existence of such a colossal emptiness is deeply puzzling. Why didn't gravity fill this void with galaxies? What process could have left a hole in the cosmos of such monumental proportions? When astronomers first mapped the Boötes Void, they expected to find thousands of galaxies within its volume, based on the average density of the universe. Instead, they found only a few dozen. This is not just a slightly underpopulated region, it is a cosmic desert of unparalleled scale. The very existence of the Boötes Void, and others like it, forces cosmologists to refine their models of structure formation. These voids are not simply accidents, they are a fundamental prediction of the lambda cold dark matter model. The story begins with the tiny quantum fluctuations imprinted on the cosmic microwave background. Over billions of years, gravity amplified these fluctuations. The slightly denser regions attracted more and more matter, eventually collapsing into the filaments and nodes of the cosmic web. But this process worked in reverse for the underdense regions. The matter that was there was slowly pulled out by the gravitational attraction of the surrounding dense walls and filaments. It is a cosmic case of the rich getting richer and the poor getting poorer. The voids are the inevitable result of gravity's work, the drained basins left behind as matter flowed into the hills and mountains of the web. However, the Boötes Void is so exceptionally large that it pushes this idea to its limits. Some researchers have wondered if its formation required an additional helping hand. One intriguing possibility involves dark energy, the mysterious force driving the universe's accelerated expansion. As dark energy causes space itself to stretch at an ever-increasing rate, it can act to inflate voids, making them even larger and emptier over time. The repulsive gravity of dark energy effectively pushes galaxies apart, enhancing the natural emptying process driven by conventional gravity. In this sense, the Boötes Void might not just be a relic of the past, it could be a window into the future, a preview of a universe where dark energy has stretched the cosmic web so thin that vast emptiness becomes the dominant feature. Studying the size and distribution of voids like Boötes is therefore a crucial way to measure the strength and nature of dark energy itself. Yet the void is not completely empty. The few dozen galaxies that do call the Boötes Void home are fascinating objects in their own right. These void galaxies are like isolated islands in an immense, dark ocean. Evolving in near-total isolation, away from the violent gravitational interactions and dense gas clouds common within galaxy clusters, these galaxies have led unusually quiet lives. This isolation has likely affected their evolution. Some studies suggest that void galaxies can retain more of their primordial gas, potentially forming stars at a more steady, less explosive pace than their cousins in the crowded web. They are natural laboratories for studying galaxy evolution in its purest form, undisturbed by the complex dynamics that dominate elsewhere. These lonely galaxies raise their own set of questions. How did they end up in the void? Were they simply left behind as the void emptied out, or did they form in situ from the sparse gas that remained? Their very existence tells us that even in the most desolate places, the universe can still spark a few points of light. To truly appreciate the scale of this emptiness, imagine for a moment you are on a planet orbiting a star in one of those lone void galaxies. You look up at your night sky. It would be an experience of profound and utter blackness, without the diffuse glow of countless distant galaxies that illuminates the sky from within a cluster, and with your own galaxy having few nearby neighbors, the darkness between the stars would be almost absolute. You might see the faint, fuzzy patch of your own host galaxy stretching across the heavens, but beyond that there would be almost nothing. The concept of a constellation would be meaningless. The few stars you could see would be isolated pinpricks in an infinite black canvas. It is a view that would emphasize isolation on a scale the human mind can scarcely comprehend, a vista where the true emptiness of the universe becomes terrifyingly personal. The Boötes Void and its smaller cousins are not mere curiosities. They are crucial components of the universe's large-scale structure. They act as counterweights to the dense clusters, their immense volumes helping to define the very geometry of the cosmic web. By mapping these voids, astronomers can trace the underlying distribution of dark matter, which dictates where emptiness can persist. The pattern of voids, their sizes and shapes, serves as a fossil record of the forces that have shaped the cosmos for 13.8 billion years. They remind us that the universe's structure is defined as much by what is absent as by what is present. These great cosmic deserts are a testament to the powerful and competing forces of gravity and dark energy, and their profound emptiness challenges us to understand the limits of cosmic construction and the ultimate fate of all structure in an ever-expanding universe. While the Boötes Void presents a mystery of cosmic emptiness, our next enigma involves a star that does the exact opposite of disappearing. It captivates us by flickering in the most bizarre way imaginable. The story begins not in a professional observatory, but with the collective power of curious minds around the world. The Planet Hunters project invited the public to sift through the mountains of data collected by NASA's Kepler Space Telescope, a mission designed to find planets by spotting the tiny, periodic dips in starlight they cause as they transit or pass in front of their host stars. It was among this vast sea of light curves that a group of citizen scientists spotted something truly anomalous. One star, catalogued as KIC 8462852, displayed a pattern of dimming that defied all logic. Instead of the neat, symmetrical, and repeating dips of a planet, this star's light curve showed dramatic, irregular, and precipitous drops in brightness. There were sharp, deep declines of up to 22%, a staggering amount since even a Jupiter-sized planet would block less than 1% of a sun-like star's light, and these dips lasted for days or weeks at a time, with no discernible rhythm or pattern. It was a signal so strange that it immediately stood out as something unprecedented in the annals of astronomy. The star was soon nicknamed Tabbys star in honor of the lead scientist on the paper that first detailed its bizarre behavior, astronomer Tabitha Boyajian. Her initial task was to rule out any instrumental errors or data processing glitches, but the signal was real. As Boyajian herself described it in interviews, the light curve looked like nothing she or anyone else had ever seen. It wasn't just one type of oddity, it was a combination of several. There were those sudden, deep dimming events, but there was also a longer-term, secular dimming trend observed in archival data from the past century, suggesting the star was also gradually getting fainter over decades. This combination of short-term, chaotic dips and a long-term decline made Tabbys' star a puzzle wrapped in an enigma. The astronomical community was faced with a simple, thrilling question. What could possibly be blocking the light from this star, over 1,500 light-years away in the constellation Cygnus, in such an irregular and massive way? The hunt for an explanation launched a frenzy of scientific creativity, generating a spectrum of hypotheses ranging from the natural to the extraordinary. The first and most conservative idea involved a colossal swarm of comets, perhaps a family of exocomets numbering in the hundreds of thousands, had been gravitationally disturbed and were now orbiting the star in a dense, elliptical cloud. As these icy bodies passed in front of the star, they would vaporize, releasing vast clouds of dust and gas that could cause the observed dimming. The irregularity of the events could be explained by the chaotic nature of the swarm's distribution. While this was a plausible natural explanation, it required a number of comets on a scale far beyond anything we see in our own solar system, pushing the limits of what we consider a typical circumstellar environment. As the comet hypothesis was scrutinized, a more sensational idea captured the public's imagination: the possibility of an alien megastructure. This was not the official scientific position, but a fascinating thought experiment proposed by astronomers like Jason Wright. The concept was based on a theoretical construct known as a Dyson sphere, a hypothetical shell of solar collectors that an advanced civilization might build around its star to harness all of its energy output. If such a structure were under construction with vast, irregular panels orbiting the star, it could perfectly explain the large, aperiodic dips in brightness. The idea was compelling because it directly matched the observational data. An artificial structure would not need to follow the neat, predictable patterns of natural astronomy. However, scientists were quick to emphasize that an extraordinary claim requires extraordinary evidence. The alien megastructure hypothesis was considered highly unlikely, a last resort explanation to be explored only after all natural possibilities had been exhausted. Its primary value was in highlighting just how peculiar the star's behavior was. The real breakthrough in understanding Tabbys' star came from detailed follow-up observations across multiple wavelengths of light. When a planet transits a star, it blocks all wavelengths of light equally, creating a uniform dip. But when the obscuring object is made of tiny dust particles, something different happens. The dust scatters and absorbs shorter wavelengths of light, like blue and ultraviolet, more effectively than longer, red wavelengths. This is why our sun appears red at sunset. The dust in the atmosphere scatters the blue light away. When astronomers observed Tabbys' star during one of its major dimming events using instruments like the Los Cumbres Observatory Global Telescope Network, they found exactly this signature. The star dimmed more significantly in blue light than in red light. This wavelength-dependent dimming was the smoking gun. It strongly indicated that whatever was blocking the starlight was not a solid, opaque object like a planet or a solid megastructure, but rather a cloud of fine, microscopic dust particles. This discovery, however, did not solve the mystery, it merely refined it. We now have a strong candidate for the culprit dust, but this immediately raises a new and equally puzzling question. What is the source of this dust, and what dynamics are creating such bizarre and dramatic dimming patterns? The simple comet swarm idea struggles to explain the long-term, century-long dimming trend. Other theories have since emerged, suggesting a recent planetary collision that left a massive debris field around the star, or perhaps the ongoing disintegration of a large moon or planet being torn apart by the star's gravity. Another possibility involves the star itself. Maybe it is a young star still surrounded by a clumpy, warped remnant of its planet-forming disk, though observations suggest Tabbys star is a mature star, not a young one. The leading theory now posits that the dust is likely circumstellar, meaning it orbits the star, and that its irregular distribution is shaped by the gravitational influence of one or more unseen planets, shepherding the material into clumps and arcs that intermittently pass in front of the star from our viewpoint. The enduring lesson of Tabbys star is not just about one weird object, but about the process of discovery in the modern age. It was found by citizen scientists, highlighting the power of crowd-sourced research. Its mystery was unraveled through a global collaboration of professional and amateur astronomers who mobilized telescopes around the world for intensive monitoring. And it reminds us of the immense treasure trove of data collected by missions like Kepler. The Kepler telescope monitored over 150,000 stars continuously for 4 years. How many other strange and wonderful signals are hidden in that data, waiting for a curious eye to spot them? Tabbys star is a testament to the fact that nature is often far more creative and bizarre than our science fiction. It forces us to remain open to the unexpected, to question our assumptions, and to remember that even in an age of advanced technology, the universe is still full of surprises that challenge our understanding. Our journey through the cosmos has revealed invisible giants and phantom energies, but the evidence for these unseen components first emerged from a deceptively simple observation, one that fundamentally rewrote the rules of gravity on the largest scales. It all begins with a basic principle we think we understand from our own solar system. The planets orbit the sun, and their speeds are governed by a straightforward gravitational dance. Mercury, the innermost planet, zips around at a blistering pace, while distant, icy Neptune plods along in a slow, stately orbit. The further a planet is from the gravitational center, the slower it moves. This makes perfect sense. The sun's gravitational grip weakens with distance. For generations, astronomers assumed this same rule must apply to galaxies. The stars in a spiral galaxy, like our Milky Way, should behave like a gigantic version of our solar system. The stars near the bright, crowded center should orbit rapidly, while those far out in the sparse, dark galactic outskirts should be crawling along. It was a logical, seemingly unshakable expectation. This assumption was shattered by the meticulous work of astronomer Vera Rubin and her colleague Kent Ford in the 1970s. They turned their telescopes towards spiral galaxies similar to our own, but with a specific goal: to map out the orbital velocities of stars at different distances from the galactic center. They did this by using a spectrograph to measure the Doppler shift of the starlight. As stars orbit, the light from those moving toward us is shifted slightly toward the blue end of the spectrum, while the light from stars moving away is shifted toward the red. By carefully measuring this shift, they could calculate the star's velocity along our line of sight. What they found was not just surprising, it was revolutionary. The stars orbiting far from the galactic center were not moving slowly at all. They were whipping around at speeds nearly as high as the stars close in. When they plotted these velocities against their distance from the center, they expected to see a curve that rose steeply and then fell off, a so-called Keplerian decline. Instead, the graph was almost flat. The rotation curve remained high, far out into the galactic halo where visible stars were few and far between. As Rubin herself reflected, the data was clear and undeniable. The galaxies were rotating in a way that defied the laws of gravity as we knew them. This flat rotation curve presented an inescapable conclusion. For the outer stars to be orbiting at such high speeds, they must be feeling a much stronger gravitational pull than the visible matter could provide. The only explanation was that each galaxy was embedded within a massive, invisible halo of matter, a halo that extended far beyond the visible edge of the galaxy itself. This dark matter halo had to contain vastly more mass than all the stars, gas, and dust we could see combined. Its gravitational influence was what was keeping those high-speed outer stars from flying off into intergalactic space. Rubin's work provided the first robust, direct evidence that the universe was dominated by something we could not see. It was a discovery that transformed dark matter from a speculative idea into a central pillar of modern cosmology, forcing us to accept that the luminous universe is just a tiny fraction of what actually exists. The scientific community, faced with this dramatic evidence, had two possible paths to explain the anomaly. The first, and now mainstream, path was to accept the existence of dark matter. This meant proposing that the universe is filled with a new type of particle that interacts gravitationally but not, or only very weakly, through the other fundamental forces, making it invisible to our telescopes. This solution elegantly explained the rotation curves and, as we've seen, went on to successfully explain a host of other phenomena, from the dynamics of galaxy clusters to the bending of light by gravitational lensing. The dark matter paradigm became the foundation of our standard model of the universe. However, a small but persistent group of physicists pursued a different, more radical path. Instead of inventing a new form of matter, they asked a provocative question: what if our understanding of gravity itself is incomplete? This alternative approach is known as modified Newtonian dynamics, or MND. Proposed by physicist Mordechai Milgrom in the 1980s, MND suggests that Newton's laws of gravity work perfectly well in regions of strong gravitational field, like our solar system, but break down in regions of extremely weak acceleration, such as the outskirts of galaxies. Milgrom's idea was that gravity might behave differently when its pull becomes incredibly faint, following a modified mathematical formula that would result in stars orbiting at more or less constant speeds regardless of their distance. In this view, the flat rotation curve is not evidence of missing mass, but a direct consequence of a tweak to the law of gravity on cosmic scales. The debate between these two explanations is far from settled. Proponents of MND point out that it can remarkably well predict the rotation curves of many spiral galaxies with a single adjustment, without the need for finely tuned dark matter halos. However, the dark matter hypothesis has a significant advantage. It fits seamlessly into the larger framework of cosmology, explaining the large-scale structure of the cosmic web and the patterns in the cosmic microwave background, things that MND in its basic form struggles with. Furthermore, observations of colliding galaxy clusters like the Bullet Cluster provide what many see as a knockout blow against MND. In these collisions, the visible gas clouds slam into each other and slow down, but the gravitational lensing maps show that most of the mass has sailed right through the collision, clearly separated from the visible matter. This is exactly what you would expect if the mass were made of collisionless dark matter particles, but it is very difficult for MND to explain. The mystery of the rotation curves, therefore, remains a driving force in physics, pushing us to either definitively detect the elusive dark matter particle or to develop a more robust theory of modified gravity that can account for all the evidence. This entire story serves as a powerful lesson in the nature of scientific discovery. It demonstrates how a single, careful set of measurements, focused on a fundamental question, how do galaxies spin, can overturn centuries of understanding and force a paradigm shift in our view of the cosmos. Vera Rubin's work was not about looking for something exotic. It was about meticulously testing a basic assumption. The resulting revolution shows that the universe often hides its greatest secrets not in the bizarre and distant phenomena, but in the details of the ordinary, in the predictable motion of stars that turned out to be anything but predictable. The flat rotation curve of galaxies stands as a permanent monument to the power of observation, a reminder that our theories must always bow to the evidence, even when that evidence leads us into the darkest and most mysterious corners of reality. But if the grand, swirling patterns of galaxy rotation hint at the presence of unseen dark matter, our next mystery takes us to a far more fundamental map, one that reveals the infant universe itself. The cosmic microwave background radiation is the oldest light we can see, a snapshot of the cosmos when it was a mere 400,000 years old. To the instruments on our most advanced satellites, this afterglow appears remarkably uniform, a nearly perfect blackbody glow with temperature variations across the sky of less than 1,000th of a degree. These tiny ripples are the seeds of all future structure, the faint blueprints for galaxies and clusters. Yet within this sea of subtle fluctuations, there is one feature that stands out like a sore thumb, a cold spot so large and so pronounced that it has captivated and confounded cosmologists for years. Located in the southern constellation Eridanus, this anomaly is a vast, circular region where the temperature of the background radiation dips significantly lower than the surrounding average, a chilling departure from the expected uniformity of the early universe. The initial reaction to such an anomaly is to search for a conventional explanation within the framework of our standard cosmological model. The most promising candidate involves a phenomenon known as the integrated Sachs-Wolf effect. This occurs when light traveling across the universe passes through a region where the gravitational potential is changing due to the influence of dark energy. As a photon enters a gravitational well like that of a massive galaxy cluster, it gains energy, appearing slightly hotter or bluer. But as it climbs out, it loses that energy again, returning to its original state. However, if the well itself is evolving, if it is becoming shallower because dark energy is causing the universe to expand faster, the photon loses more energy climbing out than it gained falling in. The net result is that the photon is slightly cooler or redder when it reaches us. Now, imagine this happening on a colossal scale. If the cold spot is caused by light passing through a supervoid, an immense region of space with far fewer galaxies and less matter than average, the effect would be the opposite of a gravitational well. Photons would lose energy entering the void and gain a little back leaving it. But again, with dark energy at work, the void is expanding, so the photon doesn't quite regain all the energy it lost. The integrated effect over the vast distance of the void is a net loss of energy, making the CMB light from that direction appear colder. This elegant explanation sent astronomers on a hunt for the proposed supervoid. And indeed, detailed surveys of the galaxy distribution in the direction of the cold spot have revealed a large underdense region, a significant void. The discovery was initially encouraging. It seemed the mystery was solved. But as cosmologists crunched the numbers, a problem emerged. The void they found, while substantial, appears to be not nearly large or empty enough to account for the severe temperature drop observed in the cold spot. The observed cooling is simply too great for the size of the void we can see. It would require a void of such stupendous proportions, so vastly empty and enormous, that it would be a statistical outlier of epic proportions, a cosmic anomaly in its own right. This discrepancy between the observed cause and the dramatic effect has led some researchers to suggest that the void might extend much deeper than our current galaxy maps can detect, perhaps filled with a diffuse gas that is difficult to observe. Yet, the gap between theory and observation remains stubbornly wide. leaving the door open for far more speculative and thrilling possibilities. When conventional physics falls short, the imagination soars. The persistent severity of the cold spot has prompted cosmologists to consider explanations that venture far beyond the standard model. One of the most mind-bending proposals is that the cold spot is not an imperfection within our universe, but a bruise left by a collision with another universe. This idea arises from the multiverse theory, which suggests our cosmos is just one bubble in a vast, frothing cosmic foam of universes. In this scenario, if a neighboring universe bubble bumped up against our own in the distant past, the interaction could have transferred energy across the boundary, leaving a distinct circular imprint on the CMB of our universe. The cold spot, in this view, would be the scar of that primordial collision, a permanent fingerprint from a reality entirely separate from our own. While this idea is currently untestable and highly controversial, it highlights the profound implications of this anomaly. It forces us to confront the possibility that the ultimate explanation for the cold spot may not lie in the physics we know, but in physics we have only begun to dream of. This single cold patch on the sky, a subtle deviation in the universe's first light, serves as a powerful reminder of the limits of our knowledge. We have mapped the CMB with incredible precision, yet it still holds secrets that challenge our most fundamental assumptions. The cold spot is a tantalizing clue, a cosmic whisper that there is more to the story of our origins than we currently understand. It prompts a fascinating question. If one such imprint from beyond our observable universe might exist, what other faint signatures are hidden within the cosmic microwave background, waiting for a future generation of even more sensitive instruments to reveal them? The search for answers continues, driving the development of new telescopes and more sophisticated analyzers, all focused on deciphering the message left in the chill of deep space, a message that might just tell us that our universe is not the only one. Deep within the laboratories of our most advanced physics institutions, machines of immense complexity whirl and collide particles in a controlled frenzy, pushing the boundaries of human engineering to recreate the most extreme energies in the universe. The Large Hadron Collider, a 27-kilometer ring buried beneath the French-Swiss border, is the pinnacle of this effort, capable of accelerating protons to energies that would make them shine with the brilliance of a mosquito in flight. Yet the cosmos has been running its own particle accelerators for billions of years, and they make our terrestrial achievements seem profoundly humble. From the depths of space, subatomic particles occasionally slam into Earth's atmosphere with energies so colossal they are difficult to comprehend. These are ultra-high-energy cosmic rays, and a single one of these particles, a proton or atomic nucleus, can carry the kinetic energy of a professionally thrown baseball, all compressed into a speck smaller than an atom. They are the most energetic particles ever observed, and their existence presents a mystery that has stumped astrophysicists for decades. The challenge of studying these cosmic bullets is as immense as their power. They are incredibly rare. A single square kilometer of Earth's surface might be struck by only one such particle per century. To have any hope of catching them, scientists had to think big, very big. The result is the Pierre Auger Observatory, a colossal detector spread across 3,000 square kilometers of the Argentine pampas. It doesn't try to catch the particles directly, which is impossible as they are destroyed in the atmosphere. Instead, it watches for the aftermath. When an ultra-high-energy cosmic ray hits the top of the atmosphere, it triggers an avalanche of secondary particles, a vast shower that cascades downward at nearly the speed of light. The Auger Observatory uses thousands of large water tanks to detect these secondary particles when they reach the ground. while a suite of telescopes watches for the faint ultraviolet fluorescence light the shower produces as it develops. By combining these signals, physicists can reconstruct the energy, direction, and nature of the primary particle that started it all. As one researcher from the collaboration explained, it's like trying to understand a shooting star by studying the ripples it leaves in a pond. We are detectives reconstructing a crime scene that is 20 kilometers high and over in a microsecond. Here is where the mystery deepens into a profound cosmic contradiction. A particle with such astronomical energy is not just a passive traveler. It is a powerful cannonball barreling through a universe filled with the faint afterglow of the Big Bang, the cosmic microwave background. This radiation, which permeates all of space, acts like a thick fog for these ultra-fast particles. A proton with an energy above a certain threshold, known as the GZK cutoff after physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, who predicted it, should interact with the photons of the CMB. In a process akin to a high-speed collision, the proton would create new particles, losing a significant amount of its energy with each interaction. Over a distance of about 150 million light-years, this process would effectively drain the particle's energy, slowing it down below the ultra-high energy threshold. This creates a fundamental limit, a cosmic horizon. Any ultra-high energy cosmic ray we detect must have originated from within our local cosmic neighborhood, a relatively small volume of space on the universal scale. This is the heart of the puzzle. When the Auger Observatory and other detectors pinpoint the arrival directions of these particles, they scan the sky within this 150 million light-year horizon, searching for the cosmic engines that could have launched them. And they find nothing compelling. There are no obvious, monstrous sources sitting at the points of origin, no nearby quasars, no hyperactive galactic nuclei. No recent supernova or gamma-ray bursts line up consistently with the incoming particles. It is as if we are finding cannonballs in a field, but there is no cannon in sight. The universe, it seems, is capable of producing these unimaginably energetic particles, but it is doing so with sources that are either hidden, transient, or of a nature we have not yet even imagined. The very laws of physics that allow us to predict the GZK cutoff also tell us that the accelerators responsible must be among the most powerful and violent events in the cosmos, yet they leave no clear signature for us to find. So what cosmic catastrophe could possibly serve as nature's ultimate particle accelerator? Theorists have proposed several candidates, each more dramatic than the last. Active galactic nuclei, powered by supermassive black holes feeding on vast amounts of matter, are prime suspects. The intense magnetic fields and relativistic jets associated with these monsters could, in theory, act as a natural synchrotron, accelerating particles to incredible speeds. Another compelling candidate is the merger of neutron stars or the hypernova explosion of a supremely massive star, the same events that produce gamma-ray bursts. The shockwaves from these cataclysms could surf charged particles across space, repeatedly boosting their energy. Some have even speculated about more exotic origins, such as the decay of hypothetical super-heavy particles left over from the Big Bang, or defects in the very fabric of spacetime. But for every proposed source, there is a problem. The acceleration mechanisms are not fully understood, and the required conditions are so extreme that they push the limits of our astrophysical models. Furthermore, if these relatively common events were the source, we might expect to see a much stronger correlation between the cosmic rays and their points of origin. The search for the origin of these particles is more than just an academic quest to catalog cosmic oddities. It is a direct probe into the most extreme physical processes in the universe. By understanding how nature accelerates particles to energies millions of times beyond our capabilities, We are testing the laws of physics under conditions we can never hope to replicate in a laboratory. Each ultra-high-energy cosmic ray that strikes our atmosphere is a messenger from a cosmic battlefield, carrying encoded information about the magnetic fields it traversed and the unimaginable event that gave it birth. The ongoing mystery pushes the development of ever larger and more sensitive detectors, and even plans for space-based observatories that could look down on Earth's atmosphere to capture these rare events with even greater precision. The enigma of ultra-high-energy cosmic rays stands as a humbling reminder that for all our knowledge, the universe still holds phenomena of such raw power that they defy our current understanding, challenging us to look deeper and think bigger about the hidden forces shaping the cosmos. Just when we thought the strange tale of our first interstellar visitor was a once-in-a-lifetime event, the universe sent us a second calling card, and this one was wonderfully, comfortingly familiar. In August 2019, an amateur astronomer in Crimea named Gennady Borisov spotted a faint, fuzzy object moving across the sky. Follow-up observations soon confirmed what its trajectory screamed out loud. Like Oumuamua before it, this object was not bound by the sun's gravity. It was another traveler from the vastness between the stars, officially designated 2I/Borisov, the second interstellar object ever discovered. But where Oumuamua was an enigmatic, rocky, and largely inert oddity, Borisov was instantly recognizable. It had a clear coma, a hazy envelope of gas and dust, and it was developing a tail. It was without a doubt a comet. This was a monumental discovery. While Oumuamua opened the door to interstellar objects, Borisov flung it wide open, presenting astronomers with a textbook example of an interstellar comet, something they could study and compare directly to the comets we know from our own cosmic backyard. The arrival of Borisov sparked a level of excitement in the astronomical community that was distinct from the bewildered intrigue surrounding Oumuamua. Here was an object they understood. As one planetary scientist involved in the observations remarked, "With Borisov, we knew exactly what we were looking at." It was like finally meeting a pen pal you've only heard stories about. The familiarity was immediate and profound. Telescopes around the world and in space, including the Hubble Space Telescope, swiveled to track the visitor as it made its closest approach to the Sun. They analyzed its light through spectrographs, breaking it down into a chemical fingerprint. What they found was astonishing in its normality. The comet was outgassing cyanogen gas and diatomic carbon, common components of solar system comets. Most importantly, they detected water vapor, the ratio of water vapor to other gases, the very essence of its composition, was strikingly similar to what we see in comets from our own Oort cloud. This was the first direct, incontrovertible evidence that the basic ingredients and processes of planetary formation are not unique to our solar system. The universe, it seems, uses a common recipe book. The icy planetesimals that formed in the frigid outskirts of a star system light years away were built from the same stuff as our own comets. This profound similarity, however, immediately gives rise to a compelling mystery: the object's origin story. How does a comet, a relatively fragile agglomeration of ice and dust, get ejected from its home star system? Comets typically reside in vast, distant reservoirs, like the Oort cloud that is thought to envelop our Sun. For one to become interstellar, it must be gravitationally kicked out, sent on a journey that will last for millions, perhaps billions of years. The most likely culprit is a gravitational encounter with a much larger object. Imagine a star system in its youth, with giant planets like Jupiter forming and migrating. The gravitational pull of such a planet can act like a cosmic slingshot, flinging smaller bodies from the outer regions of the system out into the galactic void. Another dramatic possibility involves a close flyby of another star through the system, its gravity disrupting the delicate cloud of comets and sending a shower of them flying in all directions. Borisov is a refugee, and its presence tells a story of dynamical chaos somewhere out in the galaxy, a tale of gravitational upheaval that occurred long before human civilization even began on Earth. Yet, Borisov also presented its own subtle peculiarities. As it neared the Sun and heated up, observations revealed that it was incredibly rich in carbon monoxide, a gas that requires extremely cold temperatures to form. The amount of carbon monoxide was significantly higher than what is typical for most solar system comets. This suggests that Borisov formed in an exceptionally cold environment, perhaps in the outer fringes of a very different kind of protoplanetary disk than our own, or around a cooler red dwarf star. It's a reminder that while the recipe may be universal, the specific conditions in each stellar kitchen can vary, leading to subtle differences in the final product. Borisov was a familiar face, but with a unique history written in its chemistry. The brief visit of 2I Borisov, which has now sped away and will never return, forces a staggering reflection on the scale of cosmic traffic. We detected 2 interstellar objects within just 2 years of each other. Our solar system is not a stationary target. It is moving through the galaxy, and these objects were simply passing through our neighborhood. If we found 2 in such a short time with our still limited sky surveys, the implication is that the space between stars must be teeming with such nomads. Current estimates suggest there could be thousands, even millions, of similar objects within the orbit of Neptune alone at any given time, most too small and dark for us to detect. Each one is a free-floating sample from another star system, a piece of a planet-forming process that happened light years away. The study of Borisov was a fleeting opportunity to perform a kind of interstellar geology, analyzing a rock from another world without ever having to send a probe across the immense gulf between stars. It confirmed that we live in a galaxy that is not only vast but also deeply interconnected, where the raw materials of worlds are constantly being exchanged, carrying with them the shared history of star birth across the Milky Way. But while the cosmos sends us messengers of immense power, the greatest puzzles are often found not in the vastness of space, but in the delicate balance of the universe's most fundamental laws. We now descend from the scale of galactic voids and cosmic rays to the quantum realm, to a mystery that is tiny in size but monumental in implication, the hierarchy problem. This enigma begins with a single number that seems profoundly wrong, the mass of the Higgs boson. The discovery of the Higgs boson in 2012 was a triumph, confirming the mechanism that gives elementary particles their mass. But this victory came with a deeply unsettling caveat. The Higgs mass is about 125 giga-electronvolts, a number that might seem arbitrary until you compare it to the Planck scale, the energy level at which gravity becomes as strong as the other fundamental forces. The Planck scale is a staggering 10 to the power of 19 giga-electronvolts, an energy so high it represents the ultimate limits of our physics. The problem is that the Higgs mass should naturally be pulled up to this immense Planck scale by quantum fluctuations, as virtual particles constantly pop in and out of existence and interact with the Higgs field. It would be as if a feather, buffeted by hurricane-force winds, somehow remained suspended perfectly still, defying the chaos around it. The fact that the Higgs mass is so comparatively small, so precariously low, seems like an impossible fine-tuning act, a cosmic coincidence that begs for an explanation. This unnatural stability is the core of the hierarchy problem, and it has driven theoretical physicists to propose some of the most imaginative ideas in modern science. The leading candidate for decades has been a concept known as supersymmetry. This elegant theory proposes that every known particle has a hidden super-partner particle. For every electron, there would be a selectron. For every quark, a squark. These superpartners would have a crucial effect on the Higgs boson. The quantum contributions from regular particles, which tend to drive the Higgs mass upward, would be perfectly cancelled out by the opposite contributions from their superpartners. Supersymmetry would act as a cosmic balancing scale, naturally protecting the Higgs mass and explaining its lightness without any need for miraculous fine-tuning. As one prominent theorist described it, supersymmetry would be a beautiful and profound extension of the laws of physics, a deeper symmetry of nature that stabilizes the entire edifice of the particle world. Furthermore, the lightest of these superpartners is a compelling candidate for the mysterious dark matter that permeates the cosmos, offering a potential solution to two great puzzles at once. Another radical solution involves rethinking the very nature of space itself. What if our universe has more than the three spatial dimensions we experience? Theories involving extra dimensions suggest that gravity, which seems incredibly weak compared to the other forces, is actually as strong as they are, but its strength is diluted because it can spread out into these hidden, compactified dimensions. In this scenario, the Planck scale isn't truly as high as we think. It's an illusion. The true energy scale of gravity could be much lower, perhaps even down near the scale of the Higgs mass itself. This would instantly dissolve the hierarchy problem because there would be no enormous gap to explain. The Higgs mass would be natural. This idea, often associated with models like the Randall-Sundrum model, paints a picture of our universe as a three-dimensional membrane or brain floating within a higher dimensional bulk with gravity leaking between them. It's a concept that sounds like science fiction, but it emerges from serious attempts to reconcile gravity with quantum mechanics. What makes the hierarchy problem so profound is that it is not an isolated issue confined to particle accelerators. It has a direct and dramatic connection to the largest scales of the cosmos through the concept of vacuum energy. The Higgs field is not just responsible for particle masses. Its energy contributes to the energy of the vacuum of space itself. When theorists calculate this contribution using the known laws of quantum physics, they get a number that is, once again, impossibly large, about 120 orders of magnitude greater than the value we observe for dark energy, the force accelerating the universe's expansion. This is arguably the worst theoretical prediction in the history of science, so the hierarchy problem is fundamentally linked to the mystery of dark energy. Solving why the Higgs mass is so small might also explain why the vacuum energy is so tiny, which in turn determines the ultimate fate of the entire universe. The laws of the infinitesimally small are inextricably woven into the destiny of the impossibly large. This is why the silence from the Large Hadron Collider is so deafening. For years, the LHC has been probing higher and higher energies, searching for the telltale signs of supersymmetry or evidence of extra dimensions. Yet so far it has found nothing. No squarks, no selectrons, no hidden dimensions have revealed themselves. This non-discovery has forced a profound crisis in particle physics. It is possible that supersymmetry exists, but that the superpartner particles are much heavier than anticipated, placing them just beyond the current reach of our colliders. Or perhaps nature has chosen a different, even more clever solution that we have not yet conceived. The absence of evidence has deepened the mystery, leaving us to wonder if the apparent fine-tuning of the Higgs mass is just a staggering coincidence, or if it points to a principle of nature so elegant and subtle that we have yet to grasp it. This forces a humbling contemplation. we are faced with the possibility that the stability of our entire reality, the fact that particles have the masses they do, allowing atoms and molecules and ultimately us to exist, rests on a razor's edge that we cannot explain. The hierarchy problem sits at the very heart of the quest for a final theory, a theory of everything that would unify quantum mechanics with general relativity. It is a stark reminder that our understanding of the cosmos is incomplete, and that the most fundamental answers may require us to look not only deeper into the atom, but also to consider the hidden architecture of space and time itself. The search for a solution is more than an academic exercise. It is a journey to understand why the universe is structured in a way that permits complexity and life to arise at all. Consider for a moment the delicate balance that makes our reality possible. The strength of gravity, the nuclear force that holds atoms together, the mass of an electron. These fundamental constants are not arbitrary numbers. They appear to be set with a precision that borders on the miraculous. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. If it were slightly weaker, galaxies and stars could never have coalesced from the primordial gas. If the strong nuclear force were a fraction of a percent different, carbon, the essential building block of life as we know it, would not be forged in the hearts of stars. This remarkable series of coincidences, where dozens of seemingly independent constants align perfectly to create a universe capable of hosting conscious observers, is known as the fine-tuning problem. It presents a profound question: is this apparent perfection a cosmic accident, or does it point toward a deeper truth about the nature of existence? This is where we encounter the Anthropic Principle, a concept that sits at the fascinating intersection of physics, philosophy, and cosmology. In its simplest form, the principle is a statement of obvious yet staggering logical necessity. It observes that the universe we are capable of observing must be compatible with our existence as observers. As the physicist Brandon Carter, who coined the term in 1973, framed it, what we can expect to observe must be restricted by the conditions necessary for our presence as observers. This isn't an explanation for the fine-tuning itself, but rather a crucial filter for interpreting the data. It reminds us that we cannot ask why the universe is the way it is from a position of random chance. We are a product of its specific conditions, and our very presence biases our perspective. Scientists and philosophers often distinguish between two flavors of this principle. The weak anthropic principle is the less controversial version. It suggests that we should not be surprised to find ourselves in a region of the universe, and at a moment in cosmic history that allows for life. The universe is immensely vast and varied. Perhaps there are vast deserts where the constants are different, or where radiation sterilizes everything. We, of course, could only arise in a habitable oasis. This is analogous to a puddle of water marveling at how perfectly the hole it sits in is shaped to accommodate its form, without considering that it was the hole that gave the puddle its shape in the first place. Our planet's location in the galactic habitable zone is a perfect example of the weak anthropic principle in action. We find ourselves in a place suitable for life because we couldn't have arisen anywhere else. The strong anthropic principle, however, takes a much more radical stance. It proposes that the universe must have properties that allow life to arise at some point in its history. This version moves from a statement about our location to a statement about the universe's fundamental laws. Proponents of this view, which sometimes veers into the metaphysical, argue that the constants of nature are not randomly set, but are in some way necessitated by the requirement for consciousness. This can be interpreted in different ways. Some see it as pointing toward a teleological purpose, a universe designed with the goal of producing life and mind. Others see it as a logical constraint on any possible universe that can be coherently described. The strong principle is far more speculative, as it implies that a lifeless universe is somehow an impossibility, a claim that is difficult, if not impossible, to test scientifically. The most compelling scientific resolution to the fine-tuning puzzle, one that elegantly incorporates the Anthropic Principle, returns us to the concept of the multiverse. If our universe is just one bubble in a vast, perhaps infinite, cosmic landscape, then the fine-tuning problem evaporates. In an infinite multiverse, every possible combination of physical constants and laws will be realized in some universe. There will be universes where gravity is too strong and they collapse instantly, universes where the nuclear forces are too weak and no atoms can form. Universes that are utterly dark, silent, and lifeless. But in a near-infinite array of possibilities, there will also be a tiny, tiny fraction of universes where every dial is set just right. And in those universes, conscious beings will eventually evolve, look out at their world, and marvel at the incredible odds against their existence. We, by necessity, find ourselves in one of those rare, hospitable universes. What appears to be a miracle of design is simply a consequence of a statistical selection effect. We are the winners of a cosmic lottery, and our winning ticket is our own consciousness. This line of reasoning inevitably leads to a profound and ancient question. Does the apparent fine-tuning of the universe imply a designer? For many, the exquisite balance of nature's constants is the most powerful argument for the existence of a creator, a divine architect who set the parameters with intention. This perspective offers a satisfying answer to the why behind the numbers. Yet, the multiverse hypothesis provides a naturalistic alternative that requires no designer. It replaces a purposeful creator with a vast, mindless process of cosmic proliferation. The debate between these two interpretations is not purely scientific. It is deeply philosophical, touching on our most fundamental beliefs about meaning, purpose, and our place in the cosmos. Science can tell us that the constants are fine-tuned, and it can offer mechanisms like the multiverse to explain how it could happen without design. But it cannot ultimately prove or disprove the question of why those constants have the values they do. This is the boundary where science must hand the baton to philosophy and personal reflection. The Anthropic Principle, therefore, is far more than a curious footnote in cosmology. It is a fundamental tool for reasoning about our reality. It forces us to confront the limitations of our perspective and to consider the vastness of possibilities that may lie beyond our observable horizon. Whether one sees it as a tautological truism, a gateway to the multiverse, or evidence for a guiding intelligence, its power lies in its ability to reframe the question of our existence. It connects the infinitesimal world of quantum mechanics, where constants are set, to the grand scale of cosmic structure, and finally to the intimate reality of our own conscious minds. In seeking to understand why the universe seems so perfectly tailored for life, we are ultimately exploring the deepest connection between the observer and the observed, and questioning whether the universe could ever be truly separate from the life that has emerged to comprehend it. Take a simple bar magnet, the kind you might have stuck to your refrigerator. It has two ends, a north pole and a south pole. No matter how many times you break it in half, you will never isolate a single pole. Each new piece will instantly become a complete magnet with its own north and south. This duality is a fundamental rule of magnetism as we know it, a law that seems as unbreakable as gravity. Yet, lurking within the most elegant equations of theoretical physics is a tantalizing prediction that this rule is not absolute. These equations suggest the possible existence of a magnetic monopole, a particle that would be a pure north or a pure south magnetic pole, a solitary point of magnetic charge existing entirely on its own. It is a concept that sounds like science fiction, but its discovery would revolutionize our understanding of the universe's fundamental forces. The theoretical foundation for monopoles is remarkably strong, rooted in the quest for a grand unified theory, a single framework that would merge the electromagnetic force, the weak nuclear force, and the strong nuclear force into one fundamental interaction. These grand unified theories, which describe how the forces of nature were once identical in the incredibly high-energy environment of the early universe, almost universally predict that magnetic monopoles should have been created in abundance during the cosmos's first moments. They are not an optional extra. They are a necessary consequence of the physics that seeks to explain how our complex universe of separate forces emerged from a state of perfect symmetry. But the story of the monopole goes back even further to one of the 20th century's greatest physicists, Paul Dirac. In the 1930s, Dirac demonstrated something astonishingly profound through his work in quantum mechanics. He showed that if even a single magnetic monopole existed anywhere in the universe, it would immediately explain a deep mystery that had puzzled physicists for decades: why electric charge comes only in discrete, quantized units. The electron has a specific charge, the proton has an equal and opposite charge, but why that specific value? Dirac proved that the mere existence of a monopole would force electric charge to be quantized, tying together the theories of electricity and magnetism in a beautifully simple way. As he famously stated, the quantization of charge would be explained as a consequence of the existence of a magnetic pole, a revelation that would make the universe seem more coherent and interconnected. This powerful theoretical argument launched a decades-long, worldwide hunt for these elusive particles. Scientists have employed incredibly creative methods to find them. They have sifted through moon rocks and deep-sea sediments, hoping a monopole might have become trapped there over billions of years. They have built sophisticated detectors in deep underground laboratories, waiting for the unique, immense signature of a monopole passing through and leaving a trail of ionization far greater than any other known particle. They have even used the entire Earth as a detector, monitoring the planet's magnetic field for a sudden, inexplicable jump that would signal a monopole's passage. Yet, despite these heroic and persistent efforts, not a single confirmed magnetic monopole has ever been found. The universe, it seems, is completely devoid of them in our local neighborhood, presenting a glaring contradiction between the compelling predictions of theory and the stubborn silence of observation. This absence is not just a minor puzzle, it became a major crisis for cosmology in the late 1970s. The grand unified theories predicted that monopoles would be extraordinarily massive, perhaps as heavy as 10 to the power of 16 protons, and that they would have been produced in such staggering numbers in the early universe that their gravitational influence would have overwhelmed everything else. There should be so many monopoles today that they would have long since caused the universe to collapse back in on itself under their collective weight. The fact that our universe is old, expanding, and apparently monopole-free meant something was seriously wrong with the theory. This monopole problem was one of the key motivations for the development of a radical new idea, cosmic inflation. The theory of inflation proposes that the universe underwent a brief, fantastically rapid period of exponential expansion when it was only a tiny fraction of a second old. This inflationary burst would have stretched space itself by a factor of at least 10 to the power of 26 in an instant. This incredible expansion provides the perfect solution to the monopole problem. It would have diluted the density of any primordial monopoles to such an undetectably low level that finding one would be like searching for a specific grain of sand on all the beaches of Earth. The monopoles are still out there, according to this theory, but they are now so incredibly rare and scattered across such an immense volume that the chance of one ever passing through our observable universe is vanishingly small. In this way, the failure to find a monopole, rather than being a defeat for physics, became a powerful piece of evidence in support of the inflationary model of the Big Bang. This enduring search forces a profound reflection on the nature of discovery. If a particle as fundamental as the magnetic monopole predicted by our most elegant theories can remain hidden for nearly a century despite our most determined efforts, what other cornerstone particles or forces might be eluding our experiments? Are there components of reality so rare, so subtle, or so confined to conditions we cannot replicate that they lie permanently beyond our current grasp? The quest for the magnetic monopole is far from over. It remains a holy grail of particle physics. Finding one would not only validate decades of theoretical work and confirm a key aspect of grand unification, but it would open a direct window into the universe's first moments, a time of unimaginable energy and symmetry, offering a glimpse of the true unity that underlies the seemingly separate forces that shape our world today. After the brilliant flash of the cosmic microwave background faded into the expanding darkness, the universe entered its most profound and silent chapter. For millions of years, a deep cosmic gloom prevailed. This was the cosmic dark ages, a time when the universe was a vast, featureless sea of neutral hydrogen and helium gas. With no stars or galaxies yet born, there were no sources of visible light. The cosmos was not only dark but also opaque. The abundant neutral hydrogen atoms readily absorbed the high-energy ultraviolet light that would eventually break them apart. It was a simple, elemental universe, cooling and expanding in shadow, waiting for a spark that would, quite literally, bring it into the light. This long night finally ended with a dramatic transformation, a process known as the Epoch of Reionization, when the universe woke up and became the transparent, star-filled cosmos we observe today. The key to understanding this great transition lies in a fundamental change to the hydrogen gas that filled all of space. A neutral hydrogen atom consists of a single proton and a single electron. To ionize, it means to strip away that electron, creating a free proton and a free electron. This requires a significant amount of energy, specifically photons of ultraviolet light. As the first stars and galaxies ignited, they acted as cosmic ultraviolet light bulbs, flooding their surroundings with this ionizing radiation. One by one, and then in growing waves, these bubbles of ionized gas began to appear around the earliest sources of light. Over time, these bubbles expanded and overlapped, like rising air bubbles in a glass of water, until the entire universe was once again filled with a diffuse, ionized plasma, a state it has remained in ever since. This reionization process effectively cleared the fog, making the universe transparent to light and allowing photons to travel across billions of light years without being absorbed. But how can we possibly study an event that occurred over 13 billion years ago? Astronomers use a clever trick of cosmic geometry, turning the most luminous objects in the universe into backlights. As the brilliant light from distant quasars, the active cores of supermassive black holes in early galaxies, travels toward us, it passes through the intergalactic hydrogen gas that lies in its path. By the time this light reaches our telescopes, it carries a unique fingerprint. When the universe was still filled with neutral hydrogen, that gas acted like a thick fog, completely absorbing the quasar's light at very specific ultraviolet wavelengths. This creates a phenomenon known as the Gunn-Peterson trough, a dramatic and nearly complete blackout in the quasar's spectrum at those wavelengths. As one researcher explained, finding this trough in the light of a very distant quasar is like seeing a street lamp through a heavy fog. The fact that you can't see its true color tells you just how thick the fog is. By analyzing the spectra of quasars at different distances, and therefore from different look-back times, astronomers have been able to map the timeline of reionization. The evidence suggests it was not an instantaneous event, but a gradual process that began around 400 million years after the Big Bang and was largely complete by the time the universe was about 1 billion years old. This timeline, however, presents a central mystery that is the focus of intense scientific debate. What were the primary engines of reionization? What specific objects produced the immense flood of ultraviolet photons required to ionize the entire cosmos? The suspects are few but powerful. The first and most obvious candidates are the first generations of massive stars. These early stars were behemoths, containing much larger amounts of hydrogen and helium than stars today, and they burned ferociously hot and bright, emitting copious amounts of ionizing UV radiation. However, there is a problem. These stars were also very short-lived, exploding as supernova after only a few million years. Could their brief, brilliant lives have provided enough sustained energy to complete the job? This leads to the second suspect, early galaxies. While individual stars are powerful, it is the collective output of billions of stars within a galaxy that might have been the dominant force. But here, too, there are complications. Much of the ionizing radiation produced inside a galaxy can be absorbed by its own dense gas and dust before it ever escapes to affect the wider intergalactic medium. The efficiency with which galaxies can actually leak their ionizing photons into space is a critical and poorly understood factor. Did most early galaxies have channels cleared by stellar winds or supernova that allowed this crucial radiation to stream out? The third and most extreme candidate is quasars. Powered by supermassive black holes, quasars are undeniably the most powerful ionizing sources in the universe. A single quasar can outshine an entire galaxy of stars. The mystery is one of timing and numbers. Were there enough quasars active during the first billion years to contribute significantly to reionization, or did the majority of them turn on only after the process was already well underway? Determining the relative contribution of each of these sources, massive stars, dwarf galaxies, and quasars, is like a cosmic detective story, where the clues are buried in the faint light of the most distant objects we can see. This is precisely where the James Webb Space Telescope enters the scene, revolutionizing our ability to peer into this pivotal era. Webb's powerful infrared eyes are uniquely suited to looking back in time to when the first galaxies were forming. Its mission is to directly observe these infant galaxies, to measure their numbers, their sizes, and crucially, the properties of their light. By analyzing the spectra of these incredibly faint objects, astronomers can now search for the specific signatures of ionizing radiation leaking from them. They can count how many there were and estimate how much ultraviolet light they were producing. Already, Webb has begun to identify a surprising abundance of small, faint galaxies in the very early universe, suggesting that their collective output may have been far greater than previously thought. Each new deep field image is like turning up the resolution on a blurry photograph of the universe's childhood, allowing us to see the key players in the drama of reionization with unprecedented clarity. To truly grasp the significance of this epoch, try to imagine the universe lighting up for the first time. It would not have been like flipping a switch. It would have been a slow, beautiful dawn. The first bubbles of ionized gas would have glowed with a soft, pinkish light from the recombination of hydrogen atoms. these isolated islands of light would have grown steadily, their edges eating into the neutral darkness until they merged into a brilliant, transparent web. This was the final major transition in the universe's evolution, the moment it shed its primordial simplicity and became a structured, complex place filled with galaxies, stars, and the potential for planets and life. The Epoch of Reionization marked the end of the universe's childhood and the beginning of its maturity, setting the stage for the next 13 billion years of cosmic history. And so we arrive at the final and perhaps most personally profound mystery on our list, a question that has haunted humanity for generations and now stands as the ultimate summary of our cosmic solitude. We have journeyed through 34 enigmas, from the ghostly pull of dark matter to the faint echoes of the Big Bang, each one revealing a universe of staggering scale and complexity. A universe where the conditions for life seem to be written into its very laws, where planets number in the billions within our galaxy alone. The statistics are overwhelmingly on the side of existence. With so many stars, so many worlds in habitable zones, and with the chemistry of life appearing to be a natural cosmic process, the galaxy should be a vibrant, buzzing metropolis of intelligence. It should be filled with the radio chatter of countless civilizations, the silent voyages of their starships, the unmistakable megastructures orbiting their suns. And yet, when we train our telescopes on the heavens and listen with patient ears, we are met with a profound and unsettling silence. This glaring contradiction between the high probability of extraterrestrial intelligence and the utter lack of any evidence for it is the Fermi Paradox, named for the physicist Enrico Fermi who, during a casual lunch conversation in 1950, posed the deceptively simple question, "Where is everybody?" The power of the paradox lies in its inescapable logic. As Fermi and his colleagues discussed flying saucers over lunch, he quickly ran the numbers. Our galaxy is about 100,000 light-years across and contains hundreds of billions of stars. Even if interstellar travel is achingly slow, a civilization with just a modest head start on us could have colonized the entire Milky Way within a few tens of millions of years, a mere blink of an eye on cosmic timescales. The fact that we see no signs of such a galaxy-spanning civilization, no artifacts, no engineering on a stellar scale, forces a deeply troubling conclusion. Something must be preventing life from reaching that stage, or something must be keeping it hidden. This realization has spawned a spectrum of solutions, ranging from the terrifying to the hopeful, each one holding a mirror to our own potential future. On one end of this spectrum lies the sobering concept of the Great Filter. This hypothesis suggests that there exists at least one nearly insurmountable barrier along the path from non-life to a spacefaring civilization. The filter could lie in our past. Perhaps the origin of life itself is an event of such miraculous improbability that it has only happened once in the galaxy, here on Earth. Or maybe the leap from simple prokaryotic cells to complex eukaryotic cells, which took billions of years on our planet, is the true bottleneck. If the Great Filter is behind us, it would be wonderful news for humanity. It would mean we have already passed the hardest test and the galaxy is ours for the taking. The more frightening possibility is that the Great Filter lies in our future. This is the option that gives astronomers nightmares. It suggests that there is a wall that all advanced civilizations hit, a point of self-destruction from which none recover. This could be nuclear war, runaway artificial intelligence, ecological collapse, or some technological catastrophe we haven't even conceived of yet. In this scenario, the silence of the cosmos is a cemetery quiet, a warning that the path we are on leads to an inevitable and universal dead end. The Great Filter forces us to look at our own technological adolescence with a sense of profound responsibility, wondering if we are currently approaching the very challenge that has silenced every other voice in the galaxy. But perhaps the answer is not so grim. Maybe the problem is not that civilizations die out, but that they become something we simply cannot recognize. Our search for extraterrestrial intelligence is heavily anthropocentric. We look for radio signals like the ones we use, or for Dyson spheres that fit our concept of energy harvesting. A civilization just 1,000 years more advanced than us might have moved beyond such crude technologies entirely. Their communication might be through neutrino beams or gravitational waves, mediums we are only beginning to learn how to detect. Or their consciousness might be so different from our own, perhaps existing as a collective mind or in simulated realities, that the idea of broadcasting a simple hello to the cosmos seems as primitive to them as smoke signals do to us. They could be all around us, their artifacts saturating the galaxy, but operating in dimensions of physics or information theory so advanced that they are, for all intents and purposes, invisible. We might be like ants crawling across a superhighway, completely unaware of the civilization that built it roaring past us. This idea of being overlooked leads to more optimistic, if slightly unsettling, theories. The zoo hypothesis proposes that Earth is a designated wilderness area, a planet deliberately left untouched by a galactic community that observes us from a distance, following a strict principle of non-interference. They are waiting for us to reach a certain level of maturity, a point where we can join the cosmic conversation without destroying ourselves or being culturally overwhelmed. Another idea is the planetarium hypothesis, which suggests that the observable universe itself is a sophisticated simulation, a facade created by a post-biological civilization. The stars we see and the laws we study are not the real thing, but a curated experience, explaining why the universe appears so perfectly tuned for life yet so empty of it. In this view, we are not alone. We are merely in a cage so vast we mistake it for the entirety of existence. Then there is the simplest explanation of all, the sheer, mind-numbing vastness of space and time. The galaxy is immense, and civilizations might be incredibly rare and transient. Their signals might wash over Earth for only a brief window, a few centuries out of billions of years. We have only been listening systematically for a few decades. It is entirely possible that 1,000 years ago, a powerful beacon was aimed directly at our solar system, but there was no one here with a radio telescope to hear it. Or 1,000 years from now, a signal might arrive long after our civilization has turned its attention elsewhere. We are like a person who dips a cup into the ocean for a single second and, finding no fish, concludes the sea is empty. The distances are so great that even if civilizations are common, they may simply be too far apart for their timelines to ever overlap in a meaningful way, each one blooming and fading in isolation, never knowing the others were there. The Fermi Paradox, therefore, is not a single question but a doorway into a labyrinth of possibilities about life, intelligence, and destiny. It encapsulates the profound mystery of our place in the cosmos like no other. It forces us to confront the ultimate question: are we a miracle, the first and only spark of consciousness in a silent universe? Are we pioneers on the cusp of discovering that the galaxy is teeming with life waiting to be found? Or are we simply naive, lacking the perspective to see the evidence that is right in front of us, listening for whispers in a conversation that has long since moved to a language we cannot yet speak? The search for an answer is more than a scientific endeavor. It is a quest to understand what it means to be a thinking being in a universe that seems poised between overwhelming fertility and utter loneliness. The silence is not an answer, but an invitation to keep listening, to keep searching, and to keep wondering. And so, after this extraordinary journey through 35 of the universe's most profound secrets, we find ourselves standing at the edge of a vast ocean of knowledge, gazing out at an even vaster sea of the unknown. We have ventured from the ghostly tug of dark matter that sculpts the cosmos to the phantom push of dark energy that tears it apart. We have listened for lone cries in the void like the wow signal and watched the universe's strobe lights in the fleeting brilliance of fast radio bursts. We have charted the great cosmic attractors pulling our galaxy and marveled at the intricate architecture of the cosmic web. We have peered back in time to the universe's first stars and first black holes, and we have contemplated its ultimate fate, from heat death to a possible rebirth. Each one of these enigmas, from the quantum scale of the hierarchy problem to the philosophical depths of the Fermi Paradox, is far more than a standalone puzzle. Each is a single thread in a grand, interconnected tapestry, a chapter in a single, continuous cosmic story that began with the Big Bang and continues to unfold with every question we ask. The true revelation here is not just the individual mysteries, but the hidden connections that bind them together. Think of it as a cosmic domino effect. Solving the mystery of dark matter wouldn't just tell us what makes up most of the universe's mass. It would unlock the secrets of galaxy formation, revealing exactly how those initial fluctuations in the early universe grew into the magnificent structures we see today. Understanding the true nature of dark energy wouldn't merely tell us the universe's fate. It is inextricably linked to the vacuum energy and the hierarchy problem, connecting the largest scales of the cosmos to the smallest rules of quantum physics. The hunt for the first stars is also the hunt for the origin of the heavy elements that make up our bodies. The study of supermassive black holes is intimately tied to the evolution of the galaxies they inhabit. There are no isolated islands of ignorance. Every question answered sends ripples across the entire pool of our understanding, often revealing new and deeper questions in the process. This interconnectedness is a testament to the underlying unity of physics, a hint that a simpler, more elegant set of rules governs everything from the spin of an electron to the spin of a galaxy. This grand quest for understanding brings us back to the words of Carl Sagan, whose spirit has guided this exploration. He reminded us that the cosmos is within us. We are a way for the universe to know itself. This is not merely a poetic sentiment, it is a profound scientific truth. The calcium in our bones, the iron in our blood, was forged in the hearts of long-dead stars. The laws of physics that we are unraveling are the same laws that govern the motion of every planet and the expansion of space itself. In seeking to decipher the universe, we are ultimately engaged in an act of self-discovery. We are the universe becoming conscious, turning its gaze inward to contemplate its own origin, its own nature, and its own destiny. Every telescope pointed at the sky, every particle collider buried underground, is an extension of this innate human drive to comprehend our place in the grand scheme of things. As we stand on the shoulders of giants like Vera Rubin and Stephen Hawking, we can't help but look forward and wonder what comes next. What will be the great discovery that rewrites our textbooks? Will it be the direct detection of a dark matter particle in a deep underground lab, finally revealing the hidden majority of the cosmos? Will the James Webb Space Telescope capture the unmistakable light of a population 3 star, showing us the very first dawn? Could a revolutionary new theory of quantum gravity emerge, seamlessly uniting the world of the very small with the realm of the very large and resolving paradoxes like the fate of information in a black hole? Or will the most shocking revelation come from the search for extraterrestrial intelligence, a signal so clear and deliberate that it forever answers the question of whether we are alone. The next paradigm shift is waiting just beyond the current horizon of our knowledge, in a place we cannot yet imagine. It will likely be something so unexpected that it will force us to once again reevaluate everything we think we know, reminding us that the universe is not only stranger than we imagine, but stranger than we can imagine. This endless cycle of question and discovery is the very engine of science, and it is this restless, insatiable curiosity that propels us forward into the darkness, armed with nothing but the light of reason. And so our journey through the void comes to a close, but the true revelation is that the journey itself never ends. We have wandered through a cosmos dominated by the unseen, where the ghostly pull of dark matter acts as the invisible architect of reality, and the phantom force of dark energy stretches the very fabric of space at an ever-increasing rate. We have witnessed the universe's capacity for both breathtaking violence and exquisite beauty, from the stellar cataclysms of gamma-ray bursts to the perfect, metronomic ticking of pulsars. And we have confronted the most profound questions of all, pondering the fine-tuning of physical constants, the eerie silence of the cosmos, and the very meaning of our existence within this grand, mysterious tapestry. The overarching lesson is unmistakable. The vast, dark emptiness of space is an illusion. The void is not empty at all. It is a dynamic, secret-filled expanse, a cosmic ocean teeming with puzzles that challenge the limits of our perception and invite the curiosity of every generation. This endless quest for understanding is perhaps the most defining trait of our species. It is a thread that connects the first human who looked up at the night sky in wonder to the teams of scientists who today operate billion-dollar telescopes and particle colliders. We are driven by an insatiable need to know, to push back the boundary of the unknown piece by piece. Every mystery solved is a testament to human ingenuity, but it also unveils new, deeper layers of questions, ensuring that the well of wonder will never run dry. The universe, in its infinite complexity, is a perpetual invitation to explore, to learn, and to grow. It reminds us that the state of not knowing is not a failure, but a starting point, the very fuel for discovery. In the film Contact, a beautiful sentiment captures this perfectly. Jodie Foster's character, an astronomer who has spent her life searching the heavens for a sign, reflects on the sheer scale of it all. She says, "The universe is a pretty big place. If it's just us, it seems like an awful waste of space." This line resonates because it speaks to a fundamental hope, a belief that the cosmos is brimming with potential. That waste of space is an illusion. It is filled with the raw materials for stars, planets, and perhaps other minds contemplating the same silent depths. But her words also underscore our profound responsibility. We are the universe become self-aware, the means by which it questions itself. Our curiosity is not a trivial pastime, it is a vital part of the cosmic story. So, as we conclude this exploration of 35 intergalactic mysteries, the most important step remains your own. Keep looking up, keep questioning. Let the mysteries we've discussed today be a beginning, not an end. What was the most compelling enigma for you? Was it the baffling acceleration of the universe, the strange tumbling of Oumuamua, or the haunting question of the Fermi Paradox? Share your thoughts in the comments below. Let's continue this conversation and this shared sense of wonder together. If you're eager for more journeys to the edge of understanding, make sure to subscribe and hit the notification bell so you don't miss our next adventure into the unknown. Ultimately, this quest for knowledge is about more than just compiling facts or solving puzzles. It connects us to the very essence of what it means to be human. It is an expression of hope, a declaration that even in the face of a vast and seemingly indifferent cosmos, our desire to understand, to find meaning, and to connect is a powerful and enduring force. The secrets of the universe are waiting not just for powerful telescopes, but for any curious mind willing to look up and ask, what if the greatest discovery is always the next